Well, welcome to MV Tutors. My name is Figa Manana, and we are now doing the June 2022 Physical Science paper number 2, the chemistry part. So, this is the supplementary exam that you just wrote, and if you're watching this to prepare for your next exam, then you came to the right place. Okay, stick around, and hopefully by the end of this lesson, this memo rather, you would have known how to answer all these questions. So, without any further ado, let's get right into question number 1. It's a little bit long, but we'll try to smash it as quickly as possible. Okay, so question 1 says, which one of the following compounds has the lowest melting point? Okay, so what you need to know about this topic is the intermolecular forces between each one of these compounds, how strong they are or how weak they are, because they will affect the melting point. So the stronger the force, the higher the melting point. So we need to know what those forces there. So when we look at hexane has how many bonds? It has hex stands for 6. Okay, so I'm sorry, let me write that down. It has 6. Okay, let me make that a little bit thicker. Okay, it has 6. Ethane has 2. Butane has 4. Octane has 8. Right. So the one with the lowest is the one with which has the lowest melting point. So that would be B. So then we can straight away go 1.1. The answer is B. Now for more on that, actually let me just show you something where you can get, if you need a refresher course on that. So you would just go to YouTube, put MV Tutors there, MV Tutors, there it is. Okay, and what you want to do is click on that icon there, and then it will bring you here. Go to playlists, because we have a lot of playlists here. Now we want the chemistry part. There we go. View full playlist of grade 12 chemistry lessons. Okay, and now we want the particular one that's going to help you with this. It's IUPAC, naming of compounds. So you probably watched that one right over there. Oh, it's already there. Prop is 3, but is 4, pent is 5, 6 is hex, and there we go. Oct is 8. So if you watch this lesson, it will help you to understand this question even further. Okay, let's go to the next question, which is this one, 1.2. When that is converted to that, the type of reaction is, now normally what I like to do with multiple choice questions, I don't do the elimination unless it's absolutely critical. I just try to answer the question as it is first, and then I look at the options that have been given to see what's going on. So basically what I can see here is that there was a breaking of a bond, and not just that, but more hydrogen was added. Okay, as you can see here, we had 2 hydrogens and 2, that's 4. This side we have 3 and 3, so that's 6. There was an increase in hydrogens, so that is called hydrogenation. Okay, so when I go to my options there excuse me, My throat is a bit dry. But when I look at my options there, hydration, that's not the addition of, that hydrolysis is not, halogenation, definitely not. So there is the answer that I had picked for myself. So then 1.2, the answer is a D. All right, 1.3 now says which one of the following compounds in solution will change the color of bromethanol blue. Okay, so what we know about bromethanol, this is just theory now, is that if we have an acid, okay, is that if we have an acid, let's go blue. If we have an acid will change it to yellow. That's just purely theoretical. Should know this by theory, that the blue, an acid will change the blue into a yellow. So what we are looking for here really is an acid, and we know the functional group of an acid is COOH. So anything with COOH, that's the answer. Okay, so this one, this functional group here, that's not it. That's not COH. There's COOH. So that should be our answer over there. This one, not. That's definitely not. So our only answer is the functional group for an acid, and that's it. That's purely theoretical now. And the answer is B. Okay, let's go to the next one. Okay, let's do 1.4 now. It says two different samples of impure that of equal masses react with that of that. Assume that the impurities do not react. The graph below shows the volume of that produced for each reaction. Okay, so we are looking at the volume of carbon dioxide produced versus time. Reaction number 1 gives us this graph. Reaction 2 gives us that graph. What we can notice very obviously is that reaction 2 produced more carbon dioxide than reaction 1. So here it says, when compared to reaction 2, which one of the following statements best explains the curve obtained for reaction 1? So they just want to know under what scenario will you get this difference of reactions. Okay, so the temperature is higher in reaction 1. So temperature does not affect the yield, the amount of yield. It just affects the rate of reaction, how fast or slow the reaction is gonna occur, but not the yield. Okay, so definitely not. You can cancel that out. I need a pen. And then the surface area is greater in reaction 2. Also, increasing surface area affects the rate of reaction, not the amount of yield. So the greater the surface area, the greater the rate of reaction, but not the amount of yield. So now the amount of impurities is greater in reaction 2. Okay, so they said assume that the impurities do not react. So if you have more substance that is not reacting, then the production will be less, not more, of carbon dioxide. Okay, because you're still working with the same volume. So D then says the amount of impurities is greater in reaction 1. So in reaction 1, the amount of impurities is greater than okay, so this one was wrong. It's greater than the stuff that actually does react to produce carbon dioxide, which means it's going to give a lesser production. So D is our answer, because the more impurities, look at it like this. If that is what's giving carbon dioxide, and that's the amount of impurities, only this is reacting, that means you'll get a lesser yield. Okay, so our answer then in 1.4 is D. Good. And then 1.5, 1.5 says the equation below represents a hypothetical reaction. A plus B C is equals to C, and it's a reverse reaction, and it's exothermic. Okay, it's exothermic. And then the activation energy for the reverse reaction is that. Okay, which one of the following is the activation energy for the forward reaction? Okay, so just like I said, I like to calculate it myself before I look at the options. So let's go for calculations right this side. This is now 1.5. So this is the forward reaction is exothermic, meaning that our graph really it looks like this. This is an exothermic reaction, and that minus 50 is really just the difference from there to there, from the products to the reactants. That's the minus 50. So because you say product minus reactants, products are lower than the reactants, so you get a minus 50, but the difference is 50. And then they said the activation energy for the reverse reaction. So for the reverse reaction, that means is from here to there. That now is the 110. Okay, so now they want to know which one of the following is the activation energy for the forward reaction. So they want to know now for the forward reaction, which is this from down here, from the reactants to up there. So as you can see, it's just gonna be a simple calculation of 110 minus 50, and our answer is gonna be 60. Okay, so then back here we've established that the correct answer is 60, and that is B. Okay, so we go for B over there, 1.5. Okay, let's do 1.6 now. It says a reaction reaches equilibrium at 25 degrees Celsius in a flask according to the following balanced equation. There is a balanced equation there, and it's endothermic. The forward reaction is endothermic. Which one of the following will change the color of the mixture from pink to blue? So it's going to change from pink to blue if there is more production, if the forward reaction is favored rather. So we're going to look for a scenario that is going to favor the forward reaction. Okay, so let's see. If we add water, is that going to favor the forward reaction? No, because if we add water, it's going to favor the backward reaction, the reverse reaction. Okay, because remember, according to the Chatelains, if you add something, or if you change a reaction, if you change the reaction somehow, the reaction itself will try to counter that change by doing the opposite, something like that. We'll get to the Chatelains. So now If we add water, it will favor the reverse, because the opposite of adding water is it will favor the reaction that's going to use up the water. Okay, so if I add water to this reaction here, it's affecting, it's favoring the reverse. If I cool the flask, according to the principles of Le Chatelier's, again, cooling favors the reaction that is exothermic. Okay, so since the forward reaction is endothermic, that means the reverse reaction is exothermic, which means that the reverse again is being favored because you're cooling, reducing the temperature. Okay, what about adding this? Okay, so let's go look what happens when we add that. If we add that sodium, let's see what's going to be affected over here. Okay, if we add sodium, it's not gonna favor the forward reaction, because there's nothing that's being eaten up. There's no sodium up here, and you know, it's not gonna work out. But now, if you add that, now these ions, there is chloride ions in there, and those chloride ions will react with those ions there, those chloride ions there, and what's going to happen is that the forward reaction will be favored, thus achieving what we are really looking for here. Okay, so I just want to separate, I don't want to call the whole thing, I'm just looking at the ions, because we have the chloride ions there, and I saw chloride ions there, so I know if I add more chloride ions, it's going to favor the forward reaction, thus being blue. I hope that made sense, because I'm really trying not to sound too technical here. I'm trying to bring this down to a level that's more understandable. See, I'm not even calling the compounds by their full names. I'm just using this and that, because I don't want to use too much jargon. Alright, so our answer is D. And then 1.7 says dilute nitric acid is added to distilled water at 25 degrees Celsius. How will this affect the hydronium ion concentration? There's the hydronium ions, they give them there, and the ionization constant of water at 25 degrees Celsius. Okay, so let's really try to understand what's going on here. Okay, so first of all, temperature is the same, it's at 25, so we are dealing with dilute nitric acid is added to distilled water. We're taking acid, putting it inside water. Good. Now, what does the question want? How will this affect the hydronium ion concentration? Oh, okay. And the ionization constant. Okay, so what's going to happen here is that let's start with the ionization constant of water. So the constant, because the temperature has not changed, it will remain the same. Okay, because temperature has not changed. And remember what changes equilibrium constant is temperature as well, but because there's been no change in temperature, the constant ionization constant rather of water will not change. Okay, remain the same. Now remember, you are taking an acid and you are adding it to water. So how will this affect the hydronium ion concentration? Okay, so remember there's hydronium and you're putting it in water, so the hydronium concentration, by theory, it should increase. Okay, because you're adding it, right? Adding it to water, and there's hydronium ions there in water already, and you're adding more acid which has hydronium ions already. The combination of those will increase the concentration of hydronium ions. So we are looking for a scenario where the hydronium ions are increasing and the ionization constant of water remains the same. Is that A? No. Is that B? No. Is that C? Yes, because there's an increase on hydronium ions and remaining the same of water ionization constant. So 1.7, we're going for C. Cool. Now 1.8, consider the ionization reaction 1 and 2. Okay, we take that and that X, okay, 2, the same X, and you get that and that. Now this you should know from your own theory as well, as to what is scope lab, as to what's going on here. So before we look at, well, they do want X and Y. Before we look at the options here, let's just write it out based on the theory that we know. Okay, we know that when you react H2PO4, okay, let's copy negative up there, H2O, it's a reverse reaction, and it gives you, this is what we know, that it gives you H3O, or just H, and it's plus. And then here, what we have here at the end right here, I hope you see this, is that we are going to get HPO4, and you do a cross multiplication here of these ionization, and then you will get that it's gonna be a 2 minus. Okay, and then we take that same thing, that HPO4 2 minus, and then what did we add? We add water again, H2O to it. It's also a reaction. It's a very weak reaction because it's a weak, I think it's a weak acid, so it doesn't ionize completely. We get that H3O, which is always plus, and then here at the end here, what you get theoretically, we know that you get PO4. Okay, and is it what? 3 minus. Okay, so we are going to look for this scenario then on the options that we're given. Is it A? We've got that HP2 minus. Yes, so we are looking for, that's X and that's the Y. Yes, PO and 3. Oh, look at that, it's the first one, it's A. Okay, and if you want to look at the others, but for your sake, okay, B, the Y is wrong. In C, the X is wrong. In D, the X is right, but the Y is wrong. Right. Okay, so we're sticking with A. Okay, let's look at question 1.9 now. Let's change that color. Alright. What did I do? 1.9. So, an electrochemical cell was set up using that half cell and another half cell under standard conditions. Which one of the following half cells, when connected to that half cell, will result in the highest cell potential? Okay, so this is the same thing as that. Okay, so we cell potential. Okay, so we need to go get the formula for cell potential. Let's go to the formula sheet. There we go. It's E cell potential is equals to E potential for oxidizing agent minus the one for the reducing reagent. Okay, so for those ones we need to go to table 4A, I think. Yes, 4A. Okay, and as you can see, we have here, if you read the English here, it says increasing strength of oxidizing agent, meaning the higher one is the oxidizing agent. Okay, and that was Hg. In simple terms, I don't want to use the technical term, so I'll just call it Hg. Okay, don't worry about this confusion of a line in the middle. That's just meant to confuse you. The main point is that we're dealing with Hg there. Okay, so where's Hg? Let's find it. There it is. There it is right there. Hg has a potential of positive 0.85. 0.85 is positive, minus the reducing one. Now let's go to the question. The first one is aluminium. Let's go look at aluminium. How's it doing? Where is it? Aluminium is not there. Let's see, is it here? Where is it? Aluminium, where are you? Oh, there you are. It has a potential of negative 1.66, so we get negative 1.66. Okay, let me put this in a calculator real quickly and let's see what we get. This is for aluminium. So we have 0.85 minus negative 1.66. You can put that in brackets if you want. You get 2.51. Okay, now let's go look at the next one. Zinc. Zn. Said I don't want to use technical terms. So Zn, we're just looking for Zn here. There it is. There's a potential of negative 0.76. So for zinc, so oxidizing once again, that's 0.8. I said it's what is it? Zinc is negative 0.76. Let's see what we get in a calculator for that. So it's 0.85 minus negative 0.76, 1.61. Cool. Let's go see the next one. It's CO. So we're going to be looking for CO. CO there, I see it is negative 0.28. So for CO, oxidizing once again is 0.85 minus negative 0.28. Put that in a calculator once again. 0.85 minus negative 0.28, and we get 1.13. Okay, now let's take a look at the last one. Okay, the last one has PT, which is a solid, so that's not going to help us. The gas is going to help us. That's what we're looking for. So H is what we're working with now. Okay, so it's 0.85 minus, we gotta go check out H now. Let's check out H here on our table. Where is H? Let's go down a little bit. Come on. Ah, there it is. H is 0.000. So okay, so now if we go back to the question said which one of the following half cells when connected to that half cell will result in the highest cell potential. So now we're just looking for the highest one between all these answers, and we can see that the highest one is this one of AL. So AL is A, so that's our answer there, A. So we'll choose we choose A over there. Cool. Now let's take a look then at the final question, which is 1.10. Okay. The final question says the following reaction takes place in an electrochemical cell. What's an electrochemical cell? It's a reaction that has electricity involved there. Whether electricity is being applied so that the reaction happens, or electricity is being produced by that reaction. But there's electricity involved. Now it's that copper one. It's copper and chloride, Cu and that. So now they say which one of the following is correct for this cell. Now there's a few things we need to understand about this. So remember I said I like to answer the question before I look at the options I've been given, so that applies here. So let's say that's the solution we've been given. Okay, these ones are positive, and then this one will be negative, and then this is gonna be, now for copper we know that there's gonna be a battery theoretically involved here, so we've got a battery there, right? Now the ions that are in this solution, okay, I just want to separate it into its ions. We've got copper ions, which are positive, and they are attracted to the negative rod, right? And then we've got the chloride ions, which are negative and are attracted to the positive rod, because opposites attract, right? Okay, so this by definition, because electricity is required for the reaction to happen, is an electrolytic cell. Electrolytic cell. It's not galvanic, because galvanic means the opposite, produces electricity. So there we go. Now we can go to the options then. Okay, which one of the following is correct for this cell? A, it is a galvanic cell. Definitely not, because it's an electrolytic cell. Electricity is required for it to occur. A power source is needed. Definitely, this is correct. Power source is needed. That's the battery, because it's electrolytic. The reaction is spontaneous. It is not spontaneous because it requires electricity. Okay, if it was spontaneous, that's a reaction that doesn't require any electricity. Copper acts as the oxidizing agent. No, not really, because that should be the copper ion. I said oxidizing agent. Let's see where copper stands here. No, it's up here, but these are copper ions, not copper. So not really. It might sound like it's correct, but it's not the actual copper. It's copper ions. If maybe they said ions, it would be correct. So B is more correct. I guess I was just biased of B. Everything else seemed wrong to me. So that's it. Those are the questions we have for this for this question number 1. And I hope you did understand, but in the event that you didn't, please do view our video lessons. Go to our playlist like I showed you in the beginning, and you will find a whole lot of them that will help you with all of these questions in detail. Okay, other than that, that's it from me. Please like and subscribe to our channel so that you can get future notification of our content. Okay, well, I appreciate you, and it's goodbye from me. Welcome to MV Tutors. My name is Figa Manana, and we are still doing the 2022 June supplementary physical science paper 2 now. This is chemistry's part, and we're now in question number 2. So if this is what you're looking for, stick around, and you'll be satisfied by the end of this session. Okay, well, let's get right into it. Question 2 says the letters A to H in the table below represent 8 organic compounds. Right, now it says write down the letter that represents a compound that is a ketone. Okay, now if you don't understand what a ketone is, I just want to show you something real quickly. Okay, so you just go there, you search for MV Tutors on your YouTube, and you press that icon over there. That's our MV Tutors icon. Go to playlists right there, and then we're gonna look for the chemistry lessons. There we go. View full playlist. Now we've got different ones, but for the ketone one, that's a particular one that will help you with the ketones video lessons. But you will learn from that what ketones are. Okay, but for now, let's just go and see a ketone. So ketone has that suffix there. It has that suffix on, so we're looking for on. Nothing there. No. There's an on there on E, so we're going to choose So 2.1.1, our answer is E. Okay, now this one says has the general formula CnH2n minus 2. Okay, so that's an alkyne. Okay, for more on that, you can go on our videos. Once again, I've got a video on alkynes. There it is, this one here, alkynes. I'm sure you can see it, it's even written alkynes there. So you go there just for a refresher course on alkynes. Okay, so we'll look for an alkyne here. Which one of these is going to be an alkyne? So this is an alkyne. It has a functional group, or rather a suffix of "-ine". Okay, so there we go. That's 2.1.2, and we went with F. Cool. For more on that, go to a video. Okay. Okay, which one is an isomer of 2-methyl-butene? Okay, so you need to learn about isomers here. For more on that in detail, once again, go to our channel. We've got a video on isomers. Let me just find it. Where is it? Might have passed it. Okay, no. Alcohols, IUPAC, rates of reaction. Oh my. I thought we had a video on isomers. We should have one. Oh, there it is. How to recognize different isomers. There we go. It's 13 minutes. So you can view that as well. It'll remind you what isomers are. And then based on that, 2.1.3, we're going to look for an isomer of that. Okay, and we will know then that the isomer of that, let's see, this is an "-ine", right? It's an "-ine", so that's probably a clue. We're looking for an alkene as well, and we have an alkene here in C. There we go. So, and it's a pent. Pent means 5. Here it's a but plus a meth, which is 4 plus 1. That's 5 too. So we're going with C. So 2. Let's use a different color. So red. So 2.1.4. We're going with no man, it's 2.1.3. I was fine. So we said an isomer is C. Okay, 2.1.4 has the same molecular formula as methyl ethanoate. Okay, so what is this? Ethanoate. For more on this, you need to go view our video as well. Which one exactly? The one on acids and esters. There we go. Difference between carboxylic acids and esters. They are pretty much similar in terms of they are isomers, I think. But watch that video, it will remind you. It's a very good one. Okay, so which one? Ethanoate. So we are really looking for an acid because this is an ester. So an acid has a functional group of COOH. A no, B no, C no, D no, E no, F no, G, and the answer is there's COOH over there. Okay, so it's H. we'll go for H over this side. We'll go for H. Okay, cool. Now it says 2.2.1, write down the IUPAC name of compound A. For more on that, go to our channel again. There's videos on IUPAC naming of organic compounds. Just view that one. It will remind you if you do not know how to do IUPAC names. But let us smash it. Let's smash it ourselves. Let's go black. Okay, so now we are on 2.2.1. So of compound A. What do we know about compound A? We can see that it's got how many C's? It's got 1, 2, 3, 4, 5, 6. So the longest chain is 6. 1, 2, 3, 4, 5, 6. So whether we start 1, 2, 3, 4, 5, it doesn't matter where you start. It's still going to have 6. So it's and it's an alkane because it's all single bonds. So 6 represents hex. It's a hexane, right? But we're gonna start numbering it 2, 3, 4, 5, 6. We're gonna start numbering it this side 1, 2, 3, 4, 5, 6, and then it's got a bromo on the second one. So we're gonna call it, and it's on 2 bromo. Okay, and then what else does it have? It has a methyl group there on position 2. Okay, and then it's got another one on position 4. Look at me writing 4. But there's another one on 3 as well. Let me just see. It's 1, 2, 3, 4. Oh no. The 4 one is at the bottom. Mistaken. 4, and then the other methyl group is on 5, position 5. Okay, it's like this. Right? So I've got position 2, position 4, position 5. There's 5 of them. I mean, there's 3 of them. So this is a tri-methyl. Trimethyl, and we said it's a hexane. Like that. So it's a 2-bromo, 2,4,5 trimethyl hexane. There we go. And then 2.1.2 has the general formula CN that. So this is an alkyne. You can go check out our video once again on alkynes. Where is it? There it is, there. And you will see that the general formula for alkynes is that. So we're going to look for an answer, wait, where are we? General formula. No, I'm not there. 2.2.2. I should write these things down because now I'm the one getting stuck. It's 2.2.2 because now I was looking at 2.1.2. What's the general formula of that? No. So we're looking for structural formula for compound F. Oh, it's still an alkyne. Alkene. I'll say alkene. Okay, so what are we gonna do? What do we know? It's a pent, meaning pent means 5. So let's start with 5 of carbon atoms, and I want to name them. That's 1, that's 2, 3, 4, 5. Cool. So what do we know? On position 4 and 4 we have 2 methyls. So because it's a dimethyl, so I've got a methyl group there and another one there, and tine. Okay, what do I know about a tine? An alkyne, it's got 3 bonds, so I'll put 3 right there. How's that? Cool. Now I can just complete with the H's, because all of them must have 4 bonds each. Let's count. It's got 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then 1, 2, 3, 4. This one 1, 2, 3, 4. This one 1, 2, 3. It needs one more 4, so one of them has to go. That one. Cool. That's it. Structural formula of compound F. Now let's go for 2.3. It says for compound D, right down there. Let's go look for compound D. So we're really talking about D there. Okay, so what do we know about compound D? It's an aldehyde. For more on that, go to our video again on aldehydes. Where is it? It's one of those difference ones. Oh, difference between aldehyde and ketone, because I think they are isomers. That's why I put them like this. Aldehydes and ketones. So view that video over there. They'll help you to, if you don't understand what aldehydes are. Okay, so homologous series to which it belongs to, we've already spoken about it. It's an aldehyde because of that functional group there. Because of that functional group, it makes it a aldehyde, right? Okay, so let's go. It's 2.3.1. Homologous series to which it belongs to, it's an aldehyde. Okay, and then now let's go for 2.3.2. I know I'm not concentrating much today. 2. Name of its functional group. Okay, that we call this group a carbolene group. Carbolene. These spellings they dribble me sometimes. It's a carbolene. Carbonly. Ooh, okay. Anyway, it's a carbonly. Sorry about that. I just don't know how to pronounce this. Because I can't pronounce it, I'm struggling with the spelling. It's either this or it's carbonil. Ah, my goodness. Yeah, you're gonna have to check the spelling here because I'm not entirely sure, but what we can do very quickly, let's go confirm it while I have Google over here. Should I? No, let's not do it. It's fine. It's fine. You get the right spelling. Let's move on. 2.3.3. Structural formula of its functional isomer. Okay, so go back to that video. It will help you, and you will know that the functional group of it is basically it has a, it's like that. Okay, but basically no, this would be, okay, let me show you something. You see, I said a difference between carboxylic acids and esters, and then I said difference between aldehydes and ketones. Okay, so I said this one is an aldehyde. The ketone one is the one that is like this. The difference with the aldehyde is that here almost I'd have a C and then I'd have the H, but it's like this. So it would the functional group would go to one of the middle ones for an aldehyde, but for ketone it goes to the last, either the first or the last carbon. Alright, okay, let's move on. And now here 2.4, for compound G, write down the IUPAC name of a chain isomer. Compound G. Okay, I don't want to get lost, so let me just write where we are for now. Okay, so we are in 2.4.1, and the IUPAC name of chain isomer G is G. It's fine. Oh, so G is butane, which means it's got 4. But now 3 plus 1 equals 4. So a methyl plus a propane will equal 4. So then we can say methyl propane. Okay, the alkanes. Cool. So for more on that, just go view the video on alkanes. And then the last one says a balanced equation using molecular formulae for its complete combustion. Okay, so first of all, you need to understand what combustion is, right? This is now 2.4.2. Combustion, we're just adding oxygen. Okay, so we'll take the butane and add oxygen to it. So we'll take butane. Butane is given by C4, because there's 4 of them. It's an alkane, H10. And remember, we are adding oxygen, so that we are going to get, what are we going to get? We're going to get carbon dioxide and water. Okay, so now we want to balance this. We always start with balancing the carbon. We've got 4 this side, we've got 1 here, so I'll put 4 there to make it 4. And then we need to balance the H. We've got 10 this side and we've got 2 this side. So to make this one 10, we need to put a 5 here. Okay, now we can balance the oxygen. We've got 2 this side we've got 4, times 2, so that's 6 plus 5. We've got 4 times 2. 4 times 2 is 8, not 6. It's 8 plus 5, so that's 13 this side. This side we've got 2. So to make it 13, it would have to be like 6.5, because that's 13. 6.5 times 2, that gives you 13. But we don't like decimals. Okay, so what we're gonna do is that we're gonna multiply everything by 2, so that you know, the 6.5 becomes a whole number. We want integers, whole numbers, not decimals. So if I multiply this by 2, I'm gonna be left with 2 C4 H10 plus 13 O2. That's going to be giving me 4 times 2, that's going to be 8 CO2 plus 5 times 2, that's going to be 10 H2O. Okay, now everything balances. Everything balances. We can count it. Number of C's, this side we've got 8, this side we've got 8. Number of H, we've got 10 times 2, that's 20. This side as well, 10 times 2, that's 20. And then O's, this side we've got 13 times 2, it's 26. This side we've got 2 times 8, which is 2 times 8 is 16, plus 10 is 26. So everything is balanced now. That's the balance equation they wanted. Well, that's all I have. I hope you understood everything, but in the event that you didn't, please do go check out our videos that I showed you on YouTube. They will help you. Okay, other than that, please do like and subscribe to our channel. We do appreciate that, and it will help you as well to receive future uploads from us. Okay, well, that's it. I appreciate you and enjoy the rest of your day. Well, welcome to MV Tutors. My name is Fila Manana, and we're still doing the 2022 June Supplementary exam. This is paper number 2, and we are on question number 3 of the physical science chemistry part. Okay, so if this is what you're looking for, you came to the right place. Stick around, and hopefully by the end of this session, you will be satisfied with this memo. Okay, so let's check it out. It says learners investigate factors that influence the boiling point of organic compounds. The boiling points of some organic compounds obtained are as shown in the table. Okay, so what do we see? We've got propane, butane, pentane, and so on, and we've got the masses, their molar masses, and then we've got their boiling point. Okay, first question 3.1. Let's go 3.1. It says define the term boiling point. Okay, I just want to say that if you want a recap on the lesson for this, I want to show you something. If you go to your YouTube, go search MV Tutors. Okay, click on that icon. Now this is important. Go to the playlists. Okay, press the playlist and then scroll down, look for chemistry lessons. There they are. View the playlist, and the particular one that's going to help you with this part is organic compounds. This video on organic compounds, physical and chemical properties. That's the one that you want to view if you want to answer this question in detail and full totality of understanding. But basically, when they say define the term boiling point, well, that's when that's the temperature at where a liquid turns into a gas. But there are technical terms you can use if you want to sound fancy. You can say this is really just the temperature. That's the operative word, temperature. This is the temperature at which, okay, so what happens? At which the vapor pressure of a liquid equals the surrounding pressure. So when they equal the surrounding pressure, the vapor pressures are equal, what starts happening? The transition starts happening. Okay, transition where a liquid turns into a gas or a vapor, and liquid changes to vapor or gas. It's up to you. This is a fancy one, but even if you write it's the temperature at where a liquid turns into a gas, that's good enough. Okay, 3.2.1. Okay, 3.2.1. The boiling points of compounds A, B, and C are compared. So we're looking at A, B, and C at this point. These ones. Okay, what do you notice about them? Butane, they're all alkanes because you see they end with ane. Okay, how do the boiling points vary from compound A to compound B? They want us to discuss the boiling points. So propane, remember propane is 3, the chain is 3. Prop means there's 3 of them, 3 carbons, and then this one has 4, and then pent has 5. So as you really increase as you increase the carbon there, intermolecular force is also increasing. You see that the boiling point also increases because it moves from a negative 42 to negative 0.5 to 36, so it's also increasing. So they say choose from increases, decreases, or remains the same. Okay, so it increases. Okay, and then 3.2.2 says explain the answer to question 3.2.1. So we can say then that this is what I was just saying, that the longer the carbon chain, really, I want to say carbon chain. Okay, the longer the carbon chain, you can see that the longer the carbon chain, the higher the boiling point. The higher the boiling point. And why is this? Okay, why do we have this relationship? That video that I showed you will help you, but I am going to write it now. Okay, so this is because the intermolecular forces intermolecular forces also increase between the bonds. Okay, between the bonds. Go watch the video, but basically all it's saying is that if this if I've got the propane here, I've got two intermolecular forces there, but with butane, okay, look at this, I've got 1 2 3. Well, there's more, because I mean we've got H's as well, but this is just to demonstrate that the intermolecular forces are also getting larger, more, and that requires more energy to break them. That's why the boiling point increases as the carbon chain increases. That's it. Okay, and then 3.4. 3. Did we go 3.3? What is this? We should go to 3.3. So 3.3 says the boiling points of compounds B, C, and D are compared. So now we are really comparing B, C, and D. So we're comparing B, C, D, these ones. No, I need to change the color, but it's fine. Is this a fair comparison? Choose from yes or no, give a reason. So BCD, B is a butane, pentane, methyl butane. Okay, so this is also a alkane. So yes, it's fair, they are all alkanes. Yes, so that's our answer, and the reason, they are all alkanes. That's it. Okay, the boiling points 3.4 now. Let me write it down first before I forget it. 3.4.1. The boiling points of compounds E and F are compared. So comparing E and F now. Right there. Cool. State the independent variable for this comparison. Okay, so what do I have here that would be independent? I guess let's just say if you well, I don't want to sound on like a broken record, but that video will help you if you don't know this theory already. The intermolecular forces, intermolecular forces should be independent, are the independent variables, because here these are really I think they might be isomers. Okay, so let me just check here. If you go to the video on what's the isomer of alcohol, ketones, alkenes, and alcohols. Yeah, well, we've got different videos here, you can check them out. But basically it will show you the difference between haloalkenes and alcohols, or carboxylic acids and esters, aldehydes and ketones. The reason we put them like this is because these are isomers, so they are pretty much close to each other. Anyway, that's E and F. Write down the name of the strongest van der Waals forces present in compound F. Okay, that video, once again, we talk about this. That's those forces between that are what we call dipole forces. Okay, these are the type of forces between if and now. All right, 3.5. Okay, 3.5. Which compound? Which compound D or E has a higher vapor pressure? Give a reason for the answer. So you're comparing D and E now. D and E. Okay, so once again, you need to watch theory video on this to understand the theory behind it. But basically, if you have the higher the boiling point, the lower the vapor pressure. Okay, meaning the lower the vapor, the lower the boiling point, the higher the vapor pressure. So we are looking for one that has really just a lower boiling point between D and E, and between 28 degrees Celsius and 78, the lower one is D. Okay, so that's our answer, D. And why? Give a reason for your answer. Because ethanol has a lower boiling point. And then you can put that theory then, which will show greater understanding on your side, that the lower the boiling point, okay, is the higher the vapor pressure. Purely theoretical, but you would have had to study a lot for this question. Okay, but like I said, which video in particular helps with this? It's this one: organic compound, not physical, organic compounds, physical and chemical properties. Okay, you will learn all of that. Well, that's it from my side. I think this is the last question. I hope you understood, but in the event you didn't, you can go view those videos on our channel. Once again, particularly this last one I just showed you now, it will really help you understand further. But please do like and subscribe to our channel. It will help you to get future uploads from us, as well as reaching out to others to receive these videos. But other than that, that's it from my side. I appreciate you watching this, and you enjoy the rest of your day.
Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at question 4 with you guys. I hope you've enjoyed looking through question 1 to 3 and you have a better understanding, alright, of all the topics addressed. Okay, so we're going to have a look at question 4. And please don't forget the drill. Please like our videos and subscribe to our channel. And please spread the word with your fellow matric friends as well as those who are rewriting. Alright, so it says study the following incomplete equations for organic reactions 1 and 2. Okay, so compounds P and Q are organic compounds, and T is an inorganic compound. Okay, and then we can have a look what's happening there at reaction 1. Okay, before we even go to the questions, let's just analyze what's going on. So basically the longest carbon chain there, all right, we have 4 carbons, and on the second or third, you tell me, is the methyl group attached to the second carbon or the third carbon? Or is the bromine atom attached to the second carbon or the third carbon? Alright, so if I look at the chain of carbons there, I see that they are, what do you call this, saturated. Okay, and if they're saturated, I have an alkane. But with the presence of a bromine atom, which is a halogen, I actually have with me a haloalkane. Alright, and what else do we have? I'm not going to put in the H atoms for now. I just want us to have a look at the things that we have. So we have sodium hydroxide, and in brackets there they wrote concentrated. It is important for them to tell us whether it's concentrated or dilute, because that makes a huge difference. Okay, and what do I mean? For those of you who have the Mind the Gap study guide, you'll see that wherever you have a reaction with sodium hydroxide, okay, if it is diluted or dilute, basically you have a substitution reaction. Okay, so you would have a haloalkane and a sodium hydroxide that has been diluted, which gives you alcohol and a salt. Okay, now if you have sodium hydroxide that is concentrated on the other hand, okay, then you have an elimination reaction. All right, so you'll have your haloalkane with sodium hydroxide that is concentrated, and it gives you an alkene and a salt. All right, so just be aware of that. Now getting back to our question, we know that the sodium is concentrated, so in this case we have an elimination reaction. Okay, please just be aware of that. If it was diluted, we would have had a substitution reaction. So elimination. Yeah, spelling. So elimination reaction. What kind of elimination reaction? Well, let's see. When you are done with this, I'm just going to put the arrow here. You're basically going to get a major product. We still probably have our 4 carbons with the methyl group. All right, and then we're going to have the salt, sodium bromine. Okay, so with this elimination, we can see that bromine was eliminated. Okay, and also we know that this product, remember one of the products, when you have concentration, when you eliminate, you're going to get an alkene. Right, remember we saw it here. Okay, so your products, when you have an elimination reaction, and the kind of elimination reaction is dehydrohalogenation. Okay, so you're basically taking out a bromine and a hydrogen atom, which is a hydrohalogen. Yes, hydrohalogen. So if you remove it out, the kind of elimination process there would be dehydrohalogenation, because you're taking out a halogen and you're taking out a hydrogen. So in this case, you'll be left with an alkene, because if you're eliminating something, you're bound to have more than one bond. Okay, so you have in your products an alkene, okay, and a salt. All right, but we also have an inorganic compound there. All right, so we have a salt, sodium bromide. All right, and that inorganic compound. So let us see. Because here, this elimination reaction, we just saw, if you have a haloalkane, basically dehydro, you're taking out one hydrogen and you're taking out a halogen, dehydrohalogenation. Okay, that's the kind of elimination reaction we're dealing with. Now the question comes to say, okay, I have a bromine atom, right? I have all these hydrogen atoms over there. If I'm gonna take out a bromine atom, that's easy. I took it out on the second or third carbon. And I need to take out a hydrogen. Where am I going to get that hydrogen from? Am I going to take it on the same carbon I took out the bromine atom? You can't do that, because if you take out one of the hydrogens, remember one of the products needs to be an alkene. So if you take out hydrogen on the same carbon you took out bromine, then you're going to have a double bond on one side of the carbon and a single bond on the other side. But remember, carbon has to always have 4 bonds to it. So we can't take out hydrogen on the same carbon we took out bromine. So where else do we take it? Okay, we are left with 3 carbons to choose from. We have this one, the one with the methyl, and that one there. So the carbons at the end, they are sort of like primary carbons. Those bonds are strong. For you to take out a hydrogen from there, you gotta be very brave. Okay, but you would know in your notes that there is a procedure if you want to take away a hydrogen, or you need to add a hydrogen. But in this case, we're looking at elimination. Okay, and in this procedure, I actually took a screenshot. I hope I can find it quickly. Yeah, no, not that. I took a screenshot. Okay, so we have the pronunciation. These look like Russian names. We have Zaitsev's rule, and we also have Markovnikov. No, Markovnikov. Oh my goodness. So we have Zaitsev's rule and Markovnikov's rule. And basically, when you are eliminating, you're gonna look at Zaitsev's rule. If you are adding, then you're gonna look at that name, Markovnikov's rule. Okay, so we're gonna focus on Zaitsev's rule, which says that if more than one elimination product is possible, the major product is formed when the H atom is removed from the C atom with the least H atoms bonded to it. So that is our guide there. What we are going to use, or what the carbon we're going to look at, is the one with the least hydrogens to it. So already at the ends, all right, we have 3 hydrogen atoms on the carbons at the end. But if we move in closer, I told you that we can't really take the H atom from the carbon that has the bromine atom. We're taking too much. We're being too much now. So the one that we can actually take from is the carbon that has the methyl group. So we can take away this hydrogen here. Okay, that's what Zaitsev's rule says. You're going to take away the hydrogen atom from the carbon that has the least. All right, so that would be that. So our double bond will form here. Okay, and as it forms here, we need to have again 1 bond, so that around carbon there's 4 bonds, and then we have our hydrogen atoms there. Here we're going to have 1 hydrogen, okay, and then we have our 3 hydrogen atoms over there. So we have an alkene, all right? And yeah, and now I feel like we can even name it and see where we're going to start counting. We're going to start counting from here to say this is 1, 2, 3, 4. No, in this case we have a methyl group. Okay, so instead of starting from the right, we're going to start from the left. Okay, so this is 1, that's 2, that's 3, and that's 4. All right, so it will be a 2-methyl 2-methyl butane, right? But not butane, it's butene. But-2-ene. Okay, because it is but because of 4 carbon atoms. We have a methyl group and we have a double bond at carbon 2. Okay, so now we have the major product, which is P. All right. What did we take out? We took out bromine and a hydrogen atom. all right? And remember, sodium was attached to a hydroxyl group. So we have a hydroxyl group and we have that hydrogen atom there, okay? We have the bromine and the sodium, so that's already accounted for, that's the salt. So it remains that T will be water, and water is an inorganic compound, all right? Yeah, so basically we have analyzed reaction 1. We can answer questions for reaction 1, and this should flow. All right, let's see. 4.1.1. Write down the type of reaction that takes place. We've already said it. It is an elimination reaction, okay? And if you want to expand further, you can say it's a dehydrohalogenation, okay? And then 4.1.2, the IUPAC name for compound B, we've already done it. It's 2-methyl-but-2-ene, all right? And then 4.1.3, name or formula of compound T, we've already said it. It's water, or if you like, H2O. All right, so we are done with reaction 1. We can go and discuss reaction 2. What is happening there? So we have a carbon atom attached to another carbon atom, guys. As soon as I see Cu, I know I'm dealing with an acid. All right, so I have a double bond to oxygen, and then I have an OH group. Actually, the correct way of writing it is to have O and a bond there, H, okay? And then on this side, we have our 3 hydrogen atoms surrounding the carbon. So because we have 2 carbons, this would be ethanoic acid, okay? And then we have compound Q, all right? Then the product is butyl ethanoate, okay? So I'm excited when I see ethanoate because this tells me that I have an ester, okay? And butyl, well, the ethanoate part is the carboxylic acid part, okay? Hence ethanoate, so we have ethanoic acid. The butyl part tells me that we have an alcohol. So Q is an alcohol. And how does that alcohol look? Well, it has 4 carbon atoms, but, remember. And it's an alcohol. So I have O here, and I have H there. Sorry about that. I had to take an important call. Okay, so we have an alcohol. We know that we have 4 carbon atoms, and we have an OH group there because it's an alcohol. All right, and then we have hydrogen atoms there. Yeah, and what is that alcohol's name? It is a butanol. Okay, it's a primary alcohol. All right, so whenever you have ethanoic acid, or whenever you have a carboxylic acid with an alcohol, you get an ester. Okay, and the name of the ester actually gives you hints. All right, the O8 part tells you about the carboxylic acid, and then the description in front of the O8 gives you the alcohol name or expression. Okay, so yes, so we have butyl ethanoate. And how does that look? If you were to draw a structure for butyl ethanoate, how would that look? Okay, so let me do it this way. So let me rewrite this ethanoic acid, okay, such that it fits. We have a double bond, we have O, and we have H. And on the other hand, you have your carbons, all right? We have an O and we have an H. Okay, and you have your hydrogen atoms over there. I'm not gonna draw them out now. So basically, your products of the carboxylic acid and the alcohol will be ester as well as water. So now that we know that water will be one of the products, we can take it out. So I would suggest that you draw your ester, or when you're forming your ester, maybe it's better if you have the alcohol this side and the carboxylic acid this side, but I drew it the other way. Either way, it'll give you the same answer. Okay, so now what are we left with if we take out water? Well, basically, let me just start with the the butyl, okay, the alcohol part. So I have 1, 2, 3, 4. I have that O, remember? And then I have the carbon from the carboxylic acid, okay? And basically that is how your ester will look. Okay, we have butyl and we have ethanoate. Butyl dash ethanoate. Ethanoate with the 2 carbon atoms. Okay, so that's basically the structure, if you may, for the ester. Alright guys, I know I'm taking time, but I think it's quite important that you understand this. And if you do, by all means, you can fast forward to the answer. Alright, and then we have water, okay? So that water that we took out, it is there. Alright, so now we can answer the questions. We've drawn the structures, we know what's going on, we are ready for whatever comes our way, okay? 4.1.4. For reaction 2, write down 2 reaction conditions needed. Okay, so when you're looking at forming an ester, it's a process that's called esterification. Basically, you need, there should be a line there. So the reaction there, you actually need sulfuric acid and heat, okay? So for this reaction, the conditions that need to be met, you need to have the catalyst, sulfuric acid, and heat, okay? So the heat would be indicated by the delta, and that basically is the catalyst. All right, and we are done with 4.1. Now let us move over to 4.2. And you're like, what? We're not done with question 4? No, we're not done. Not yet. All right, so now it says the cracking of a long chain carbon, C10H22. So if you realize that is an alkane, right? Because of the formula that we know for alkanes, CnH2n plus 2. So if we have 10 carbon atoms, it's decane, okay? It sounds like a weird name, but yeah, it is decane. So we have the process of cracking, okay? And take place in test tube A. So all of that is taking place in test tube A. And whenever you have to crack, you're going to require a lot of energy. You're going to require a lot of heat. Because guys, remember, alkanes are saturated and saturated compounds are strong. The longer the chain, remember that? The longer the chain, the stronger the bond. Okay, so you're going to need high temperature, you're going to need high pressure, you're going to need energy to break these bonds because they're tight. Okay, so now you have cotton wool soaked in decane, and then you also have I forgot what the word is, but aluminum there with trioxide. Okay, and then this experiment was basically taking place in a lab. It's not like a hectic one that takes place in a very hectic place. Okay, so we have the aluminum and the oxygen, aluminum trioxide, I believe. And what it does, it basically is a catalyst. And what does a catalyst do? Remember, if you're looking at your graph for energy versus time, if you're gonna need like high energy, for your reaction, whether it's exothermic or endothermic, what the catalyst does, it reduces the energy that you need, okay, so that you get your reaction. So that is what the aluminum trioxide is doing. It's basically reducing the amount of energy you need. It's basically the catalyst. All right. And then what happens? So it says 2 straight chain organic compounds, X and Z, are produced in test tube A according to the following balanced equation. Okay, so we have C10. I'm not going to draw the structural formula for this, just too many atoms there, and it's in liquid form. Okay, then you have 2 times X, which is in gas form. All right, so we have X and Z that are produced. So normally during cracking, the products that you have, you'll have an alkane and an alkene. Okay, and then yeah, so 4.2.1, it says state the function of the aluminium trioxide, which is a solid in there, in the test tube. Okay, so I've said it before, it acts as a catalyst. Okay, it lowers the energy required for this reaction to occur. Okay, so yeah, it basically acts as a catalyst. And then 4.2.2, okay, so before we even get to the question, it says the organic compounds X and Z are now passed through bromine water. Okay, so it's bromine as an aqueous solution at room temperature. Okay, like I said, this is probably an experiment happening in a lab. In test tube B, okay, now only compound X reacts with bromine water. Like I said, when you have cracking, one of the products will be an alkane and the other will be an alkene. Now, alkanes do not react, especially in addition reactions. With alkanes, you either have substitution or elimination. But now, because we're adding bromine to compound X, because compound X is reacting with it, we can then safely assume, that compound X is an alkene and Z will be an alkane. Alright, now it says 4.2.2, apart from the gas bubbles being formed, state another observable change in test tube B. Okay, what I can say, bromine water, bromine in general, I don't know if they named it bromine because it has a brown color, but yes, it has a brownish color to it. Okay, and so what you're gonna see then, obviously there's that reaction where the bubbles, you have the water, the bromine water that is a bit brownish. Okay, but as this reaction of aluminum trioxide, well, it's not a reaction because aluminum trioxide is a catalyst. Catalyst doesn't react with the things that are going on there. So you have your compound decaying. Okay, so if it comes in there in liquid form into the test tube that has bromine, the reaction there will cause the color of the bromine to actually turn clear. Okay, so that's one of the things that you could observe there. Okay, and also bromine does have a distinct odor. All right, so if you want to, well, not if you want to eliminate, but through the reaction, the odor can be eliminated as well. All right, so, but I'll stick, it's 1 mark. I'll just say that the bromine water turns clear. Or clears up. It doesn't turn clear. What is that? So 4.2.3. Write down a type of reaction that takes place in test tube B. Alright, so you have an alkene and you are adding bromine to it. Okay, so that will be an addition reaction. Okay, so yeah, they didn't say name. They just said name the type of the reaction. So you either have addition, elimination, substitution, esterification, all of those things. But yeah, so basically here we have we have an addition reaction. And if you want to know in detail what kind of addition reaction it is, because you're adding bromine, it'll be halogenation. Yes, halogenation. Okay, 4.2.4, we're nearly there. Write down the molecular formula of compound Z. And then 4.2.5, write down the structural formula of compound X. Okay, guys, I kind of Googled this to say if you were to crack decane, what kind of an answer would you get? What kind of a reaction? What products will be produced? And basically, if you want to produce petrol, which is octane, you would have C8, okay, and then the other two carbon atoms would be the alkene. Okay, so you'd have an octane plus ethene. All right, but here's the thing with this question. We have gas products, okay, and I want to draw your attention to the notes that are compiled here, that whenever you have a gas product, especially with alkanes and alkenes, you can see here that the first four members of alkanes, okay, so methane, ethane, propane, butane, are gases at standard temperature and pressure. We know that this is taking place at room temperature, okay. So for the alkane portion, we can have at maximum 4 carbon atoms, which is butane. So we are limited. And also with the alkene, it says the first 3 members of the alkenes, which is ethene, propene, and butene. Those are also gases at standard temperature and pressure. So you can't have octane, what I Googled. You can't have octane as an answer. You must work out some way, somehow, how you're going to use at most 4 carbon atoms for the alkane and 4 carbon atoms for the alkene. Okay, but 4 plus 4 doesn't add to 10. And that's why you should pay close attention to the 2 in front of the X. That makes things a little bit easy. Okay, so what options do we have? If we know that X is an alkene, okay, so you have a double bond somewhere, and we know that at most you can have 4 carbons for Z, okay? So let's see, if we choose 4 carbons for the alkane portion, so basically we have butane, then what are we left with? We are left with 3 carbon atoms for the alkene, okay? Remember, there's a 2 in front, so 2 times 3 would give you 6. So you have 1, 2, 3. And somewhere there, you have a double bond. It doesn't matter whether a double bond is on the right side or the left side, because like if you count 1, 2, 3, it's still, it's still on the second carbon. So yeah, doesn't matter where you put the double bond for propene. So you would have your 10 carbon atoms, okay? But these things need to balance, right? We need to at the end have C10 and H22. So in this case here we have C4 and H, 2N, which is 8 plus 2, that's 10. So now we left with 22. So here you'd have 1, 2, 3, 4, 5, 6. And 6 times 2, that is 12. So 12 plus 10, that's 22. So this works out, okay? This works out beautifully. So then your compound X, this can be, do they want the molecular formula for compound Z? Okay, so this can be your X and that can be your Z. And that is just option 1. Another option would be, let's see, if you were to have 4 carbon atoms, all right, and you have a double bond, meaning you'd have 8. Okay, so the second option would be to have 2 carbon atoms for the alkane and 4 carbon atoms for the alkene, and you could place the double bond either here or in the middle. At the end you still have 10 carbon atoms altogether. All right, if I check here, how many hydrogen atoms do we have? Well, we basically have 6. And in this case, how many hydrogen atoms would we have? 1, 2, 3, 4, 5, 6, 7, 8. And 8 times 2, 16. 16 plus 6 is 22. So this could also work. Let's see. I'm giving options because I honestly do not know which one would actually work out. But yeah, so we had 3, we have 4 what if you chose 2? Meaning you would have 4 this side. Okay, you can't actually have this option because if you have 4 carbon atoms for the alkene, you'd have to have 6 for the alkane, and that can't work because then it won't be a gas at standard temperature and pressure. So these are basically the 2 options that you can have. Okay, so which answer are we going to take? I think either of the 2 would be okay, I think. I would take the one with the alkane that has the most carbons. Alright, so they say write down the molecular formula for compound Z. So compound Z, that is the alkane. I will go with, the butane. Okay, so butane has 4 carbons and the hydrogen carbons are 10. Okay, so that's the molecular formula. If they wanted the empirical formula, we would make it the simplest, but they asked for molecular, so that's fine. And then 4.2.5, it says write down the structural formula of compound X. So what you're gonna write down this. You don't have to show that it's actually double. I mean the 2 in front. So you can just write the main structure without multiplying it by 2. So since they want the structural formula, okay, I chose 3 carbon atoms. And I honestly went with that option as well because I don't have to figure out where the double bond is, okay? So this was like option A, and that's option B. Option B is a little bit complicated because I don't know where the double bond is in this butene. Okay, so let's just stick to simple things that don't complicate our lives. But like I said, I'm not sure what the answer is, honestly. Alright, so we have a double bond, and it doesn't matter where you put it. I could put it here even. Alright. Maybe some of you might be asking, why am I putting the arrows like that? Well, there's a topic you covered in grade 11 that talks about, the bending of the bonds. If you have, there's a whole theory behind it, but I don't think they are strict when it comes to marking, so you could put them like this, but I'm just putting it as how it would be in real life. Alright, so you have a single bond there, and here I will definitely put in the hydrogen atoms because they asked for the structural formula. Okay, and here you have how many? You have, I'm missing one, yes. Should have 6 hydrogen atoms times 2, it's 12, plus 10 is 22. Alright, and that's it. They didn't ask for the name, but this would be propene, and that would be butane. And we're done with question 4. I know I took long, but I think it was worth it, right? Thank you, and enjoy the rest of your day.
Hello everyone, and welcome to MB Tutors. I'm Solo, and we'll be looking at question 5. Alright, so you know the drill. Please do like our videos and also subscribe to our channel, and don't forget to spread the word. And I hope that paper 2 preparations are going well so far. Alright, so we are looking at question 5. Normally deals with the rate of the reactions. Okay, so it says learners use the reaction of magnesium carbonate with excess dilute hydrochloric acid to investigate the relationship between temperature and the rate of a chemical reaction. Okay, so we have a balanced equation. So we have a metal carbonate and an acid, and the reaction between them produces a salt, carbon dioxide, as well as water. Now the results obtained are represented in the graph below. Okay, let's just zoom in. Okay, there we go. Now how do you unselect? There we go. So we have the graph there. So on the y-axis, we have the average rate of production of carbon dioxide. So basically, we're looking here at the production of carbon dioxide. Okay, and temperature as well. Now you know with the rate of reaction there are various things that affect it. Okay, the concentration, the temperature, I forgot other things, but it's like 5. Surface area, a catalyst, yeah, there we go. So now answering 5.1, it says define the term rate of reaction. For as long as we have the word there, rate, it tells you that there is a time factor to it. So the rate of reaction basically is the speed at which a reaction takes place. Okay, it could take place in a very slow manner, or you can increase the rate. By increasing temperature, the rate will increase, right? By increasing the surface area, the rate will increase. By introducing a catalyst, it reduces the energy required for this reaction to take place. So those kind of things, all right? So if we were to define the term rate of reaction, is basically the rate at which a reaction takes place, the speed at which a chemical reaction takes place, right? So that's one thing I would say. Speed at which a chemical reaction takes place. Or you could also say that a reaction rate is the change of concentration per unit time. Okay, so you could say reaction rate, the change of concentration per unit time. It could be concentration, it could be volume, it could be the number of moles, but yeah, all of that we can observe it over a set period of time. Okay, then 5.2, it says state 2 conditions that must be kept constant during this investigation. Okay, so we are already measuring temperature, right? So what else can we keep constant? Well, we can keep the volume. Let's see. Okay, so we already have an amount of magnesium carbonate. It's in a solid state, so we can keep that constant. Okay, the phase, okay, of magnesium carbonate, because if it's in a solid state and you decide to make it molten liquid, or if it's like a solid block and you decide to cut it into pieces, that will affect the reaction rate. So keep the phase of magnesium carbonate the same. All right, and what else can you do? You can also keep the concentration of hydrochloric acid. Okay, concentration of hydrochloric acid, and I spoke of volume as well. So you can keep the volume, okay, of the reactants constant as well. Okay, I mentioned 3 things, but yeah, so the phase, the concentration, the volume, that will help. Okay, so that the only thing that we're really focusing on is temperature. You don't want to be measuring the rate of production of carbon dioxide only thinking that you have temperature that you're controlling, but the other things happening in the background. You want to keep other things constant so that the only focus is on temperature, so that you get accurate results and not ones that are watered down. Okay, switch off my phone, sorry. Now, use the collision theory to explain the relationship shown in the graph. So we can see with this relationship that the higher the temperature, right, the higher the rate of reaction. Okay, you can see it, it's increasing, right? So they are somewhat directly proportional. Okay, maybe let me not say directly proportional because that would have to be a straight line, but they are in relation like that. If you increase the temperature, the rate of the reaction will increase. Now, how do we use the collision theory to explain that? Okay, so first of all, you increase temperature, right? By increasing temperature, you are giving the particles of the reactants energy. Okay, so Increase in temperature results in reactants receiving energy, heat energy, and if they were not moving, they start moving. If they were already moving, the rate at which they move is now increased. Okay, so reactants receive energy and they move around. Okay, we're not really using technical terms here. Okay, and as they move around, okay, secondly, the average kinetic energy, okay, because remember, not all particles are going to receive or get that increase in temperature at the same time. Some will, come about. So I can't say all the particles increase, in speed at the same speed. So I'm going to say the average, okay? So as they move around, then the average kinetic energy increases, okay? And when the average kinetic energy increases for each particle or the reactants, then the likelihood of collision is actually more, okay? So the average kinetic energy increases for the reactants, and therefore more collisions occur. Collision, yes, it's double L and not double S. So more collisions occur. All right, and if you have, come on, if the probability of, if you have a lot of collisions, the probability of those collisions being effective is quite high. So if more collisions occur, the probability of effective increases, right? And if that's the case, then the rate of reaction also increases. Ooh, my handwriting here. But yeah, just bear with me, guys. So yeah, basically the rate of the reaction will increase. And how many marks is that? The collision theory? 4 marks. So you have to talk, right? I'm writing in point form. You can write it in a much better way. But that is basically the guide. Okay, and now, yeah, I forgot to add more pages. So sorry about that. We're gonna go to the next question, and I need more pages. So insert pages. Okay, and yeah. So we're going all the way to question 5.4. All right. It says the learners obtained the graph using a 5-gram magnesium carbonate with excess hydrochloric acid at 40 degrees. Okay. Now calculate the time taken for the reaction to run to completion. And that is a nice 6 marks. Okay. So what do we have there? If I were to just get this graph here. Okay. Okay, so at 40 degrees Celsius. Okay, so we can follow the line. Don't have a ruler here, don't mind me. Okay, so right at 40. Okay, I see that the value there will be 0.5. Okay, so the rate of reaction or the average rate of production of carbon dioxide is basically, okay, so yeah, it's basically 0.5 grams per minute, okay, at 40 degrees Celsius. Now we need to get the time taken. Remember, if you're going to get the rate of reaction, it's basically, you can even have mass. Yeah, mass over delta T. So we have the rate of reaction. We probably need to go calculate the mass. and then we can finally calculate the time. All right, so let's have a look. What do we have? What don't we have? Firstly, they told us that we have 5 grams of magnesium carbonate. Okay, now we're going to have to determine what the molar mass of magnesium is, what carbon is, and what oxygen is. I already know that oxygen is 16, carbon is 12. I'm not sure about magnesium. We'll check it out. And why are we doing that? Okay, so basically we want to know the number of moles for magnesium carbonate. Okay, and that will basically be the mass over the molar mass. So let's go have a look at what magnesium okay, so it has 24. Okay, so magnesium is 24, and let's just add that up quickly. So we have 24 plus 12. Ooh, much better calculator than the one that I normally use. Alright, so that's basically 84 grams per mole. Okay, so how many grams did we have originally? We had 5 grams. Okay, so 5 grams all over 84 grams per mole, and that will give us the number of mole. Okay, so 5 divided by 84, and that is 0.0595. Okay, please just keep this value in your calculator. Don't take it out because we're probably going to use it at some point. So now we have the number of mole for magnesium carbonate. Okay, why did we calculate that? Well, in our equation, okay, since we've been given the information about magnesium carbonate, we're going to use that to get the number of mole. Then it's already balanced, this equation, which is a nice thing. So we're going to look at the ratio. So we have 1 mole of magnesium carbonate, and if you look at carbon dioxide there, it's also 1 mole. So we can therefore say the number of mole for magnesium carbonate is actually equal to the number of mole for carbon dioxide, and therefore that is 0.0595 mole. Alright. Yeah, and yes, so we have that. Now we can get the mass of carbon dioxide, and what are we going to use the mass for? Ultimately, we're going to say the rate of reaction is equal to the mass of carbon dioxide all over the time it takes, because the question asked the time taken for the reaction to run to completion. Okay, and since the graph here is about the production of carbon dioxide, we're interested in carbon dioxide. Just out of interest, I want to see on the formula sheet if they actually do give you the rate of reaction equation. Or they're just expecting me to know that. Yeah, I think it's one of those where you kind of have to know, so it's fine. So we have the number of mole for carbon dioxide. We can definitely get the mass. So again, number of mole is equal to the mass over the molar mass. So the mass will be equal to the number of mole plus the molar mass. Now carbon dioxide, so we have carbon, it's 12, and we have oxygen, 2 of it, right? So at the end we have 12 plus, let me store this, shift, store A, just in case I need it. So we have 12 plus 2 times 16, and that is 44. So I have 44 grams per mole. Okay. And now I can get my mass. So the number of mole is 0.0595, and the mass is 44. So I can then, let me just create some space. So I made that, yes, so that multiplied by 44 will give us 2,62 grams of carbon dioxide that is basically produced. Okay, and then now we can finally calculate the rate of reaction. I'm actually going to write it out. So the rate of reaction is equal to the mass over the change in time, and therefore the time is equal to the mass times the rate of reaction. And we have that the rate of reaction that we read off the graph is 0.5 grams per minute. Okay, so let's just be aware of that. So we have 2,62 grams multiplied by 0.5 grams per minute. We need time. Okay, so if I have 0.5 grams per minute, we could be saying mole. So per minute, I'm going to actually swap it a bit. No. Yes. There's something wrong that I did here. Because I'm seeing this is not working out. Alright, so if I take the time that side, I will have mass over rate of reaction. There we go. Now it makes sense. The mass 2,62, the rate of reaction 0.5 grams per minute. And so per minute, and that's grams. So basically I'm gonna get time in minutes. Ne? So calculator out, there's the mass, we're gonna divide it by 0.5 and we get 5,24 minutes. Okay, they didn't say they wanted in seconds, they just said calculate the time. So there it is in minutes. I guess we can leave it there. And now 5.4.2, calculate the molar gas volume at 40 degrees if 1,5 cubic decimeters of carbon dioxide is collected in a syringe. Okay, so how are we going to get the molar gas volume? Okay, let's go have a look at the why am I going so slow? Formula sheet. So the molar volume, okay, so we have N, so you have the actual volume and the molar volume. Okay, so let's go back up again. Let me just pause and blow my nose. So yes, 5.4.2, the molar gas volume at 40 degrees, okay, if 1,5 cubic decimeters of carbon dioxide is collected in the syringe. And basically then we are going to substitute for our volume the 1,5 cubic decimeters, and what we're looking for is the molar volume. So let me just make that the subject of the formula. Alright, and then I'll have volume over number of moles. So what is our volume? They already gave it to us. We're thankful. 1,5 cubic decimeters. And what are the number of moles that we calculated for carbon dioxide? Well, we did that previously. It is 0.0595. I hope I stored that value. I think I did. 0.0595 mole. Okay, so this is cubic decimeters, and this is mole. So now our molar volume, our molar gas volume at 40 degrees will be, let me just check. Okay, there's the value, so it will be 1,5 divided by A, and that is basically 25,2 cubic decimeters per mole. And I don't know if you realize this, but this is actually much closer to the, no it's not. So at standard temperature, which is 25 degrees, you would get a molar volume of 22,4. I don't know, is it given here? Let's just check. Yes, 22,4 cubic decimeters per mole. But I mean, that is at standard temperature, which is 22 degrees. Now we have 40 degrees and we're getting 25. So yeah, It should be more. Alright, cool. And now lastly, we're almost done with 5.5. With question 5. So it says the graph below represents the Maxwell-Boltzmann distribution curve for carbon dioxide gas at 40 degrees. Okay, so I have done a video on that, okay, where I explain the different, what do you call this? The different scenarios. If you change this, if you do that, and I'm going to show you now. So where are our chemistry lessons? Where are the chemistry lessons? Oh, there's another page. So this is our YouTube page, or your rather YouTube channel, which you're on. So this is physics and that's chemistry. So let's have a look. And then I have done it, the Maxwell-Boltzmann distribution diagram made simple. Alrighty, so I did it for you guys, and yeah, it's weird having to look at myself. But yes, basically, I discussed the effect of temperature. What else have I discussed? Oh, still the effect of temperature. And I discussed what it actually means. So basically, at the turning point of that graph, that is your most probable energy, right? And then we have our activation energy. Once you have passed over on the other side of the activation energy, that's where effective collision occurs, okay? But in this yellow region, that's basically where the energy that the particles have is smaller than the activation energy, and it's therefore unable to react. Only after the activation energy can the particles react. But anyway, you guys can watch it in your own time. Let's get back to the question, which we haven't even read yet. So we have the Maxwell-Boltzmann distribution curve, and then it says redraw the graph. So okay, on the y-axis we have the number of particles or molecules for carbon dioxide, and then we have kinetic energy on the x-axis. So it says redraw the graph above in the answer book. Clearly label the curve as A, alright? And then on the same set of axes, sketch the curve that will be obtained for the carbon dioxide gas at 20 degrees. So what are we doing? We are reducing the temperature. I get it here, the A is 40 degrees, and then 20 degrees we are definitely decreasing. Okay, so let me just take a screenshot of it so that we can sketch and answer this question, right? Okay, got it. Now, so they haven't really put for us the, what do you call this, the activation energy. It's okay, I will put it in for us. It's fine, I wanted a ruler, but it's fine, I'll just draw freehand. Okay, so let's just say we have the activation energy and it is there. Okay, so this is our activation energy, EA, and here this is the most probable energy, right? Okay, so we said beyond the activation energy, as you go to the right, that is where the particles will react. Okay, so we're just drawing the graph. Oh, okay, that's nice. I thought we had to explain something. So this is graph A at 40 degrees Celsius. Now, how will graph B look? Okay, so remember that here, this is where our most probable energy is, okay? And therefore, when we draw the graph of B, I'm so used to my camera being there. So when we're drawing the graph of B, first of all, your most probable energy will be less than A, okay? So it will be somewhere to the left. Why? You have decreased the temperature, right? So therefore, the kinetic energy will decrease as well because there's not a lot of energy, just, it's less. So yeah, and then your most probable, the point here at 40 degrees, at 20, it will be somewhere there. Okay, so this would be B at 20 degrees. And how you would then sketch the graph, it would look something like this. Okay, yeah, so basically it will look like that. Okay, not the best looking graph. Let me try again. So let me do this, and it looks like that. Okay, that's better. So what do we see here? Our turning point is much higher. Our our most probable energy has decreased because the temperature has decreased. The area of the activation energy is smaller, okay? Meaning there are less particles that are able to react once you reduce the temperature. And most of your particles will be underneath the graph, sitting there doing absolutely nothing because they don't have energy, right? If you want them to do something, give them energy. And that's the difference between at 40 degrees and 20. At 40, after the activation energy, you had a lot of particles that are able to react, and less particles were just sitting there not doing anything. But when you reduce the temperature, first of all, like I said, the maximum probable energy, it decreases. And your turning point there, it will increase because you have taken some of the particles from where it was 40 degrees, and now we have decreased the temperature, so they have to go back, and we need space, and therefore you get the area under the graph at 20 degrees being much higher. But guys, yeah, you can definitely refer to the video that I showed you. I do explore other options or other scenarios where you have a catalyst present, or you increase the concentration, or increase the number of moles, or reduce, or whatever. I've really I've really covered quite those scenarios, so go check them out. But yeah, as for me, we are done with this question. All we had to do is sketch. How many marks? 2 marks. Yeah, 2 marks. Okay, bye guys. Enjoy the rest of your day.
Well, good day. Welcome to MV Tutors. My name is Figa Manana, and I will be doing this question number 6 now of the 2022 June supplementary physical paper, the chemistry part, paper 2. Okay, if this is what you came looking for, then you came at the right place. Stick around with me, and by the end of this, you would have understood how to do this question and others, hopefully. Okay, let's get right into it. It says initially 4 mole, that's important, 4 mole, okay, it's 4 mole, and 4 mole of H2 and 4 moles of I2, okay, so both are 4 moles, are allowed to react in a sealed 2 decimeter cubed flask according to the following balanced equation. Okay, I see the equation, and it's exothermic because enthalpy is less than 0, it's negative. The graph below shows the concentration of H2 and HI versus time during the reaction. So what you should note here is that H2 is the reactant, as you can see it from the balance equation, and HI is the product, as you can see it as well on the graph, that it starts at 0 and it ends up there. Okay, write down the value of Y. So the value of Y, if we look at Y here, if we look at the Y-axis, we see that it's concentration, and concentration is given in mole per decimeter cube. Okay, so that's giving us a clue of how to calculate for Y. So this is 6.1.1. So it's the concentration, and it's given by the number of moles over the volume. Okay, and then what's the number of moles? We were told, and it's H2. We're told 4 moles of H2, so we go 4, and the volume we were given 2 decimeter cubed. So that's a 2 there. For divide by 2, I don't need a calculator for that. I know it by head. It's just 2 mole per decimeter cube. Okay, so that's the value, that's the concentration of Y. Okay, that's it. And then it says state Le Chatelier's principle. Okay, for Le Chatelier's principle, I want to show you something that you should do. If you go to YouTube, okay, and then you just search MV tutors, there we go. Okay, and then what I want you to do is press on the icon right there, and then this is important, go to playlists. Okay, and what you want to do is go over to the grade 12 chemistry lessons. Okay, and then these are all our lessons, but the one that is specific to this one, here it is. Here's about Le Chatelier's, how to better understand chemical equilibrium. There's Le Chatelier's as well. If you just want a refresher course, this one is really extensive. You can watch it however long you desire. But anyway, I just want to show you that there's Le Chatelier's principle over there. We wrote it, so you can write this down. When equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So that's like if you increase maybe temperature, according to Le Chatelier's, the system will favor the side that will use up that temperature, okay, and so on and so forth. But the principle, this is what you write: when equilibrium in a closed system is disturbed, okay, the system will reinstate a new equilibrium by favoring a reaction that will oppose that disturbance. Okay, like when you eat too much, according to Le Chatelier's, if you become fat, your closed system will try to oppose that fat and try and eat it up, so that it opposes it basically. So there's an opposition according to Le Chatelier's principle. Okay, but that's what you write right there, what I just showed you. Okay, let's move on now. It says changes. Okay, so for 6.1.2, okay, answered. Okay, now we are on 6.1.3. It says changes were made by the temperature of the flask at time t2. Okay, yes, we can see there's a change that happened. Was the flask heated or cooled? Okay, now there is something that we should know about temperature changing according to Le Chatelier's principle. Now, if we can see, the products increased. Okay, the products increased, meaning the products were favored. Okay, now we know due to Le Chatelier's that an increase in temperature favors the endothermic because the endothermic eats up heat, but a cooling or a decrease in temperature favors the exothermic. Okay, So if you cool it, it favors the exothermic because exothermic gives off heat. Okay, so now since the forward reaction is exothermic and the forward was favored, that means there was a cooling. Okay, there was a cooling, so we are going to choose cooled over there. Okay, the system, I said choose cooled. Okay, so that's all we're going to write. And then 6.1.4 says fully explain the answer. Okay, fully explain why you say it was cooled. 6.1.4, no problem. I'm just going to do that. Okay, so just like I said, okay, according to the Chatelains, okay, let me just say according to the Chatelains, I want the space here. It's Le Chatelains. According to Le Chatelains, decreasing the temperature favors the exothermic. Okay, now when we look here at this production here, the forward reaction is exothermic. In this case, the forward reaction is exothermic. Okay, thus it is favored. Thus it is favored, meaning, you know, meaning the system was cooled. Or the flask, let's use the flask. So you write something along these lines, it makes sense, you'll get your full marks. Okay, let's go to 6.2 now. It says the equation below represents the reversible reaction that takes place when NO2 is converted to N2O4. Okay, and there it is, both gases. Initially, X mole of NO2 is sealed in a 1 decimeter container at 350 K. When equilibrium is established at this temperature, 0.81 mole of N2O4 is present in the container. Write down the meaning of reversible reaction. Once again, you can just go and watch our video if you need a refresher course in this. We speak about this extensively, but let me just write it for you. Like blue, let's go black this time. Okay, so this is 6.2.1. Write down the meaning of reversible. So this is a chemical reaction. Okay, what's up with this chemical reaction? a chemical reaction in which the reactants form products. Okay, but that's not all. Okay, which in turn, the products now, which in turn react to form reactants again. Okay, so I guess you understand it goes forward and reversibles, forward and reversible, forward and back. It just swings between products and reactants. That's it. Okay, and then it says show that the equilibrium constant for this reaction is given by that. Okay, so what I want to do then for this question 6.2.2 is that I want to do it my own way and see if it's going to give us this equation. But what we're going to do is that we're going to do the Rice method. What's the Rice method, you say? Well, let's do it right now. Just put R I C E, rice, and then I'll put a final E, but it's the same E. Okay, and then on top here I'm gonna put the reactants. The reactants we have we have NO2. Okay, and I like to put a double R to a double line to separate reactants from products. Products is N2O4, and they're both gas, so they are here. Okay, so I will fill in the information that we are given, and then we'll solve the one that we actually do not have. So here we go. Let's start with the information that we are given. What do we know? We know that actually, let's start with the ratios. There's 2 moles of that is to 1 mole of that. Okay, and also initially X mole of NO2. So initially we have an X there, is sealed in 1 decimeter container. When the container is established at the temperature, 0.81 mole of that is present. When the equilibrium is established, meaning 0.8 mole of N2O4 is present in the air. So let's go equilibrium 0.81. We put it there. Okay, I think that's all we've been given present. Now we have to move on from here. So what do we know here? Initially, when it comes to products, they always start at 0, and then you add the change. Initially, the reactants always start at something, and then you subtract the change, right? So what was added in order to get 0.81? Yes, 0.81 was added, and there is a relationship between the ratio and the change. Okay, and it's 2:1. Let's get a calculator. All we need to do is multiply 0.81 by 2, and then we get 1.62. Okay, now remember we said the relationship between, you always start with the initial number of mole and you subtract the change to get the equilibrium. So the equilibrium here is x minus 1.62. Now to convert, these are in moles, right? But this last E is a concentration, meaning we have to divide by the volume. We take the moles that are in equilibrium and we divide them by so 1.62. and what's the volume that we've been given? It's 1. Okay, you can see it over there. It's 1. So it's like pretty much it stays the same. Okay, divided by 1, it's still going to be 1. Okay, so now that we have this table, what we want is this concentration, right? So we know that actually the equilibrium constant is given by concentration of the product, right, divided by the concentration of the reactant. Okay, so in this case, the products that we have, we want the concentration of N2O4 divided by the concentration of NO2. Now look at this, the ratio is 2:1, so we always take the ratio and we can put it on top there. It's going to be a square. Alright, so the concentration of the products, there we solved it, it's 0.81, and then of that it's x minus 1.62, and it has to be squared, and there we go. Show that the equilibrium constant is that, it's the same, it's exactly the same as what we were given this side. Cool. All right, we're done with this question. Let's move on to the next one. Then it says okay, we've shown that, and then it says 0.79 moles of N2O4 is now added to the equilibrium mixture above. When the new equilibrium is established at 350 K, it is found that the amount of NO2 increased by 1.2 moles. Okay, it's a mouthful, it's a lot, but we'll take it piece by piece, no problem. Okay, so let's go for, okay, let's go for it. It's 6.2.3. okay, what I want us to do is we're gonna do that rice table again and fill in what we have and leave the rest to see if we can figure it out. So we're going for the rice method once again, right there, and we still have NO2 as our reactant, right, and then we have N2O4 as our product. Okay, so remember, now all we are doing, or all we've been told, is that there was an addition. Okay, they said 0.79 moles of NO2 is now added to the equilibrium mixture, meaning, remember, initially we had started with okay, let's go for ratios. Let's just fill those in. It's still 2:1. Then initially here we have, now it's gonna be x minus 1.62. Okay, because remember it was added to the equilibrium mixture. So now the equilibrium mixture is the initial. And also here we had what was it, 0.81, and now but it says 0.79 moles of N2O4 was added, meaning we need to add that 0.79 over there. Okay, and then they say okay, we read it, and it is found that the amount of NO2 increased by let's read. When the new equilibrium is established, it is found that the amount of NO2 increased by 1.2 moles. So that's the change. It's an increase. It's not saying that at the equilibrium is 1.2. They're saying the change by 1.2, meaning it increased by 1.2. Okay, now let's write the change for NO2. Remember we said there's a relationship between the ratio and the change. So if we say 1.2 divided by 2, we get 0.6. Okay, now remember when it comes to the equilibrium, the change for reactants we subtract them, but the change for what's this, products, we add them. Okay, so there we go. So here we basically have to say, let's get a calculator, we have to say x minus 1.6 minus 1.2. So let me put that. It's 1.62 minus 1.2, then I get 0.42. So here I'm gonna have x minus 0.42. This side, remember the change we added, so we're going to add all those numbers. 0.81 plus 0.79 plus 0.6, and then we get a total of 2.2. Okay, this is our new equilibriums now. All right, okay, so now what we need to do is figure out the concentration. Is it still the same concentration? So it's divided by 1, so we'll just leave it like that. It's divided by 1. All right, now this is the theory with this thing, is that if you look closely here, the temperature was 350, and also here it's 350, so the temperature didn't change, which means the Kc values will not change. The Kc values are exactly the same. Okay, so theoretically, if we equate the Kc value, we should be able to solve for the x. So here, what's going to be the Kc value for here? I'm not going to go through that formula. You know, it's always concentration of 2.2 divided by the concentration of the product divided by the concentration of the 0.42 of the reactants, and it's squared. Okay, good, and it's equals to the first one, this one, which was 0.81 divided by x minus 0.42. It's not 0.42 this time. It's gonna be 0, it's not even 0, it's 1.62, okay, square. Okay, so all we have to do now is just really some mathematical gymnastics. So I'm going to cross multiply, and we will have 2.2 times x minus 1.62. Now it's squared, but I just want to, put two brackets of it. Okay, just to simplify my life. And this side it's gonna be 0.81 times x minus 0.42, and I'll put two brackets as well, x minus 0.42. Okay, you might not see that last part. Now I'm just gonna continue with my gymnastics. So it's x times x, I get x squared, x times that minus 62x. I still do this exercise, 62x, and then that squared. Okay, now this one I need a calculator. What is 1.62 squared? Plus 2.6244. Okay, I don't think it'll fit this side, so I'm just gonna put it here. It's equals to 0.81, and then x times x, x squared, x times that minus 0.42 x, that minus 0.42 x, and then that, need a calculator again, 0.42 squared, that plus 0.1764. Cool. Wow. Okay, let me just multiply these in. So I'm gonna say that times that, and I'll multiply it all the way through. So I'll have 2.2 x squared, and then here these ones, let me just combine them. It's going to be minus, let me add them, it's 1.62 times 2 because there's two of them, and then okay, I don't want to confuse you, let me just say 1.62 plus 1.62, yeah? And then we get that, and then I want to take this then and multiply it with the 2.2 times 2.2, get that figure 7.128x. okay, and then plus, I need to multiply that by 2.2, 2 times that number, which is 2.6244. okay, and then I get plus 5.77368. It's okay, I'll write all of it. Now this side, I'll multiply everything inside. First one is 0.81 x squared. Let me add these two, it's gonna be minus, so 0.42 plus 0.42, and then I get that, and I take that multiplied by 0.81. okay, and then that's my final answer. 0.6804x plus, I need to take this then multiply it by 0.81, so I'll go 0.81 times that number, which was 0.1764, and then I got 0.142884. Okay, now I just want to bring everything into one equation, so I'm gonna take everything this side and bring it to the other side, meaning I'm gonna start with the x squared. I'm gonna say 2.2 minus 0.81, and then I'll have, so I have 1.39 x squared, and then this one it's negative 7.128. If I take this number to the other side, it changes from negative to positive, so I'm adding it, 0.6804, and then I get minus 6.4476x, and then the last one is a positive 5.77368 minus this one, which is 0.142884, 884, like that. Okay, so that's going to be a positive 5.630. Let me take it 4 decimal places. I'll put an 8 here. It's okay, and all of this is equals to 0 now. Now I've got one equation, right? Okay, so what I want to do then with this one equation is that I want to solve for x, and here I can only use the quadratic equation. It's mathematical gymnastics. That's why when you're doing physics, you always have to do maths. When you drop physics, you drop maths automatically. But when you when you drop maths, you have to drop physics automatically. But you can drop physics on its own and do something else like geography, whatever. But you cannot do physics without maths, because you need the maths. So there we go. If it wasn't for the maths, we wouldn't know the quadratic, equation in order to solve for x, because you remember this from mathematics. Okay, so let's go in and substitute. What's minus b? Okay, so I like to write my variables, so that's a, that's b, and that's c. So minus b, because it's negative here, so it's just going to be positive here, 6.4476 plus or minus square root of b squared, which is the same thing, 6.4476 squared minus, well, squaring doesn't matter whether it's negative or positive, it's always going to be a positive answer. 4 times a, what's a? A is 1.39, and then b, c rather, is 5.6308. Cool. Put that in a square root, divide all of this by 2 times a, What was A? 1.39. Cool, let's put this in a calculator. So it's a fraction, start on top, 6.4476, let's start with a plus, a square root of 6.4476 squared minus 4 times 1.39 times 5.6308, okay, 08, and then downstairs we're going to have 2 times 1.39. Okay, so that's our first x value. We have that x is equals to 3.47. I'm just gonna leave it at 2 decimals, or x is gonna be equals to, let's go put a negative sign there. We're just gonna scroll to the side until we get there, delete the positive and put the negative. There we go, 1.17. Okay, so these are in mod. That's it. These are final answers. Okay, we've got 2 answers, but one of them is more correct than the other one. You can always do the check, but since this number is a little bit bigger, this 3.4, I would say maybe this it's the more correct one, because if you look, if you substitute that one, 3 is bigger than the 1.62, but 1.17 is smaller than 1.162, meaning, you know, it's really gonna give you a negative value of the initial number of moles. But it really doesn't matter, because no, it does matter. So I would say then this one is the more correct one. Okay, well, I think that's the last question. Indeed it is. Oh, that was a very long question. I hope you did understand and you got to appreciate the use of mathematics in physics. But please also just go over to our videos, lessons. We have very nice summaries for all these chapters and calculations, and we've done many other previous papers as well with similar questions. So please do indulge yourself in these discoveries. Okay, well, other than that, that's it from myself. I appreciate you, and you do enjoy the rest of your day. Goodbye.
Hello everyone and welcome to MV Tutors. I'm Solo and I'll be looking at question 7 with you guys. As you can see, I'm using this paper downloaded from Stanmore Physics because the original paper I had was scanned upside down and I cannot figure out how to invert it. So but anyway, we thank Stanmore for providing it on the internet. So for those of you who are looking for the paper, just Google 2022 June exam and then you'll get yourself, or you'll find yourself in the Stanmore Physics website, and you can download the papers, because I have a lot of requests of people wanting papers. Now I must, long process. Anyway, let's get to the question and not complain. And you know the drill. Please do like our videos and subscribe to our channel. If there are inputs that you want to give us or address things, please do comment below, and we are happy to answer, to help, to assist, and to take on criticism even, because we've had people who comment and say, if only you could do it like this, why don't you try this to make it better. Please help us to help you better. All right, help us so that we can serve you better. But yes, question 7. after that mini sermon. Two acids, HX and HY, of equal concentrations are compared. The pH of HX is 2.7 and the pH of HY is 0.7. We can see that they are acids because their pH is lower than 7. Alright, so 7.1.1, it says, define an acid in terms of the Lowry-Bronsted theory. So you have the Lowry-Bronsted and you also have the Arrhenius. Before I get to the Lowry-Bronsted, which is very easy to remember, you have the Arrhenius theory, which really depends on water. Without water, you can't really define it. But basically it says in solution, particularly water, you will form hydronium ions if you have an acid. But according to the Lowry-Bronsted theory, quite an easy theorem or theory, it basically says an acid is a proton donor. So we're just going to leave it there. It is a proton donor. And then 7.1.2 says, which acid, HX or HY, is stronger? Okay, like I said, if you have a pH of 7, it's basically neutral, like water, which can be an acid in one aspect and can be a base in another, but right now it's just neutral. If you go higher than 7, all right, all the way to 14, you have a base. If you go all the way to 1, you have an acid. Okay, and so we see that the closer you are to 0, actually, the closer you are to 0, the more acidic your molecule is. And we can see that HY is 0.7, is closer to 0, right? So HY is stronger. Okay, HX is somewhere around here. It's still a strong acid, kinda, but yes. And now 7.1.3, it says acid HX ionizes in water according to the following equation. Does it ionize completely? I don't know. Had they given us, had they told us that it's a strong acid, yes, it would ionize completely, but we're not sure. I'm just saying that it is kind of a strong acid because it has an acidity or a pH of 2.7, so it's relatively there. But yes, so acid HX ionizes in water according to the following equation. All right, and then we have a Ka value for the reaction being 1.8 times 10 to the negative 5 at 25 degrees. Okay, remember Ka, similar to the Kc constant. Basically, it is the concentration of your products. So in this case, you have H3O, and also your salt, which is an anion because of a negative charge. And remember, when you're writing the equation here, you can't put solids and liquids because their value is equal to 1. We are dealing basically with the concentrations of gases and solutions. So you're only going to put there the acid, which is HX. Okay, and they tell us that the value is 1.8 rather, times 10 to the negative 5. Okay, and now they say, is the concentration of hydronium ions higher than, lower than, or equal to the concentration of HX? All right, and give a reason for your answer. Okay, so I don't know if you know this, but there's a table probably somewhere in your textbook that tells you the Ka values. The Ka values for strong acids, okay, they are like higher than 0, okay, higher than 1. All right, so basically, if this was like somewhere in the middle, Ka values that these ones are probably lower than 1. I just want to see where it starts. Okay, I have a textbook near me. I don't think I can show you actually that table, but I'm going to use another one. But basically, your weak acids or kind of weak acid. Remember, your strong acids is like your hydrochloric acid, sulfuric acid, nitric acid. So those have values, let me just say, times 10 to the power 1 and higher. Okay, so higher and equal to times 10 to the power minus 1. But your weak acids have values of, okay, so basically, yeah, they have values of less than times 10 to the power 1, but I think they have, yeah, from -1 all the way to like negative, let me see here, I have until -14. But I'm not saying it stops there, I'm just saying the table that I have. So I would then say, yeah, times 10, maybe then, yeah. I don't know what this middle value is. I'm trying to look for the middle value, but I am failing here dismally. But basically, times 10 to the power 1 higher, it means we have a strong acid which ionizes completely. But if it's times 10 to the -1 and lower, all the way, maybe even exceeding times 10 to the power -14, you have a weak acid, okay, or somewhat weak. And these ones, they don't ionize completely, okay, so doesn't ionize completely. Sorry for the noise outside. It is what it is. You asked for the memo, so please take it in with noise. So it doesn't ionize completely. So we can see with this Ka value that this is not really a strong acid. It doesn't ionize completely. Okay, so therefore the concentration, because if the concentration of hydronium was way higher, let me just show you here. Here they show you the different concentrations of hydronium, and it depends. If hydronium is a strong acid, it would be higher than times 10 to the -7. All right, if its pH is 7, then it is times 10 to the -7. If pH is higher than 7, then it is smaller than times 10 to the -7. Okay, so for hydronium, we said HX has a pH of 2,7. So yeah, it's there at like 1 times 10 to the power -3. I don't know if you can see that clearly. But yes, at a pH of like 3, between 2 and 3, you have 1 times 10 to the -2, 1 times 10 to the -3. So that would be the concentration of your hydronium, okay? But with this acid over here, so basically, if your hydronium had a high value and your acid had a low value, you would expect your Ka to be high. And that's not the case, because you have hydronium value that is quite low. And if it's low and you have a low value here, it means that the concentration of your acid is actually high. All right, so basically in this question, I hope I'm making sense, but in this question, you can therefore say the concentration of hydronium is lower than the concentration of HX, okay? Because we've showed here that we've shown here that HX actually doesn't ionize completely, and that's the reason why you have such a low Ka value. Okay, I hope that makes sense. And now let's get to 7.2. So learners add 150 cubic centimeters of sodium hydroxide solution. Okay. So learners add 150 cubic centimeters of sodium hydroxide solution of unknown concentration. So let's just write there. You have sodium hydroxide. Okay, and the volume there, I'm just going to put it in cubic decimeters. So if you're converting from cubic centimeters to cubic decimeters, you divide by 1,000. So you get 0,15 cubic decimeters. And we don't know what the concentration is, okay? We don't know what the number of moles are, so we can't exactly calculate concentration. And then, so yeah, we add the sodium hydroxide of unknown concentration to 200 cubic centimeters of that hydrochloric acid solution. So on the other hand, you have hydrochloric acid. We know that the volume is 0,15 2 cubic decimeters, and the concentration here is given 0.03 mole per cubic decimeters. And if you wanted to get the number of moles, that's pretty much easy, because concentration is equal to number of moles over volume. Therefore, number of moles is concentration times volume. It's very possible. Okay, now what are they saying? Okay, they find that the pH of the final solution is 2. So basically, during this neutralization reaction, because you have a strong acid, which is hydrochloric acid, and you have a strong base, okay, they're neutralizing one another, but at the end, your final solution is acidic. So it tells you that you had an excess of hydrochloric acid. It was just a lot of it, okay? And that makes sense. I mean, you had a higher volume. But yeah, so let's get to the questions. Oh, and they give us a balanced equation. We have it there, no need to rewrite it. You can see it, basically 1-to-1 ratios for the number of moles. Alright, now 7.2.1. Calculate the concentration of the hydronium ions in the final solution. Okay, so I hope you're happy here. It's a nice 3 marks. The hectic 7 marks is coming. So basically, if you were to use the pH calculation, just to be sure, because sometimes I tend to forget the negative. So it's basically negative log the concentration of hydronium. If we were dealing with a base and they asked for the concentration of the base, you would use POH, not pH. Okay, so what do we know? We know that the pH is 2, and then we're looking for the concentration of hydronium ion. So what I'm going to do now, I will write this equation in terms of concentration of hydronium. So what do? Basically, if I say 10 to the power of the pH, and I say, no, before I even begin, let's firstly get rid of that negative. So the negative can come this side. Okay, and I'm left with log H3O. Okay, then I want to get rid of that log. So what I do, I say 10 to the power of the negative pH, and I say 10 to the power log H3O. Why 10 to the power? Because basically if I have 10 to the power log something, the answer will be something. Okay, basically what I'm saying is, if I have 10 to the power of log 69, my answer would be 69. Okay, so 10 to the power of log something is something. All right. So basically then I am left with the concentration of H3O. Okay, because they cancel each other. And this side I have 10 to the power negative 2. So finally, the concentration of hydronium is equal to 1 over 100. 1 over 10 to the power 2, which is just basically 0.01. Concentration is mole per cubic decimeters. Okay, so that's it. And then 7.2.2, the initial concentration of sodium hydroxide. Started to get cold. The initial concentration of sodium hydroxide. So in this scenario, we had hydrochloric acid there by itself with its concentration, number of moles, volume. And then, so that was initially, right? And then you had sodium hydroxide coming with its initial volume of 150, its initial concentration, its number of moles, right? And then they mixed. So there was a reaction, but the final solution, because there was excess hydrochloric acid, because all the sodium hydroxide was used up, then you have the concentration of the hydrochloric acid. Okay, so now they want the initial concentration of sodium hydroxide. So how will I get that? What will be my process? I will calculate what I had initially for hydrochloric acid, what I had in excess for hydrochloric acid, and what I had during the reaction. I'm particularly interested in what happened during the reaction, because if I can get the number of moles for hydrochloric acid during the reaction, I can then use my ratios to get the concentration of sodium hydroxide and then use the initial volume to get the answer. Okay, all of that I put in words, I'm going to put in a calculation. So I want to know, I don't want to use concentration, because I could say initial concentration of hydrochloric acid is equal to the hydrochloric acid in the reaction plus the hydrochloric acid in excess. Okay, but the thing with concentrations is they change. Okay, but the number of moles don't change, so it's better for me to actually calculate the number of moles. So I'm gonna get the number of moles of hydrochloric acid initially. Okay, and that can be easy to calculate, because remember, I have this initially, these are initial conditions over here. So I have concentration of 0.03 and the volume of 0.2. So CV, the concentration was 0.03, the volume was 0.2. Okay, and then 0.03 times 0.2, 0.03 times 0.2, that's basically 0.006. Okay, 0.006 mole. Okay, now let's see the excess. So number of moles of hydrochloric acid in excess. That, guys, we've already calculated it. And that is 0.01 mole. And some of you are like, what? How? Oh, no. That is the concentration. Sorry. Number of moles is concentration times volume. So you know that hydrochloric acid is a strong acid, and strong acids, they ionize completely. And if they ionize completely, it means that the concentration of hydrochloric acid is equal to the concentration of hydronium. Okay, because it ionizes completely. Remember in the previous question, that other HX, it did not ionize completely, hence we couldn't say they were equal. All right. So here it ionizes completely, so the concentration would be 0.01. And the volume, guys, remember, finally, in the final solution, you had both the volume of sodium hydroxide and the volume of hydrochloric acid. So combined, you had 150, 0.15, plus 200, 0.2. All right, and then what would be the number of moles? So we have 0.01 multiplied by 0.35, and that's basically 0.035, 0.0035, and that's mole. So guys, now we can get to what we want. I can then calculate the number of moles for hydrochloric acid in solution.
Mama.
Yes, my baby.
There's pizza.
Wow, go eat it. I'm coming. Okay, go. Close the door. So now, the number of moles initially is equal to the number of moles during the reaction plus the number of moles in excess. So now I'm looking for the number of moles during the reaction. It's basically equal to the number of moles initially minus the number of moles in excess. Okay, I'm just going to use NR. Okay, so initially we had 0.06, 0.006, and then in excess we had 0.0035. And if we calculate what those number of moles are, 0.006 minus the answer, it's 0.0025 mole. Okay, now we can say during the reaction that 0.025 moles for hydrochloric acid, okay, we can see we have a 1-to-1 ratio. So the number of moles for hydrochloric acid will be equal to the number of moles for sodium hydroxide, and that's basically 0.0025 mole. We're almost there, guys. And now I can take the initial volume of sodium hydroxide to get what the initial concentration is, because the moles don't really change. What changes is concentration. So the concentration of sodium hydroxide is basically equal to the number of moles over the volume. And we have 0.0025 divided by the volume, which is 0.15. And we are going to see, so 0.15, and we have 0.02, 0.017, but rounding off to 2 decimal places, that's 0.02. And that is mole per cubic decimeters. And we're done with question 7. Yeah, you know, the more you do past papers, the more you realize some questions are actually repeated. So please try to go through past paper questions, not just this one, but others, so that you get into the flow. I think last year as well, with the 2021 paper, I had used a similar equation to get to the answer. So practice as much as you can. It'll get easier with time. All right, and that's goodbye from me. Just a reminder, guys, this is the topic of acids and bases, right? Please do visit our YouTube page. Oh, you're already there. And just pretty much go to the lessons that we have, all right? Our playlist called Grade 12 Chemistry Lessons, and there you can see on the bottom right corner, my husband there has presented the lesson on acids and bases. So you can just go through it. You really have no excuse to fail because there's so much at your disposal. It's not just us who are doing maths and physics, but obviously you're here, so stay here. But if you have other people that you can listen to and you can understand better, by all means. But yeah, so we've covered basically all the topics that you need for the matric syllabus. And you can go to it and basically empower yourself and learn. Okay, there it is. Oh.
Plus the POH. It's strong
okay, so
dissociates completely.
yes,
So
you see,
it's
dissociating
always
completely. Wabana.
under hydrolysis.
So yes, please indulge.
Dissociate.
Hello everyone and welcome back to MV Tutors. I'm Tsolo and I'll be looking at question 8 with you guys, and I'll also see you again in question 9. So yeah, you know the drill. Please do like our videos and subscribe to our channel. Now let's look at question 8, which has to do with electrochemical cells. You know that I've covered the theory in this. I'll show you now. But yeah, so an electrochemical cell is set up using an aluminium rod, okay, and gas X. Alright, so we don't know yet, is it a galvanic cell or is it an electrolytic cell? But let's see. Now it says the initial EMF measured under standard conditions is 2.89 volts. Okay guys, if EMF is positive, then you are dealing with a galvanic cell. And it's something that I have addressed in the lesson as well. Okay, so yeah, this is the galvanic cells lesson. Okay, in the chemistry lesson playlist. Alright, so if we just go back there, if I play it, then here, guys. Okay, so you can see in one of the notes that I wrote, okay, I said the EMF is always bigger than 0. So if you don't understand, please just go through the lesson and these questions will become easy. Okay, let's go back and answer. What did I do now? Ah, snap. Okay, we're back. Yeah, so let's start answering the questions. Okay, so this is question 8. 8.1. Yeah, guys, it's cold. I'm wearing my work jacket, advertising there, Jones and Partner. All right. An electrochemical cell is set up, okay, like we have read, and the initial EMF under standard conditions is 2.89 volts. All right. So yeah, the E cell, which is equal to E cathode plus E anode, it's equal to 2.89 volts. Now 8.1.1, it says state the standard conditions under which the cell operates. Okay, so when they talk about standard conditions, we are going to refer to the temperature, we're going to refer to the pressure, and we're going to refer to the concentration. Okay, the temperature is 25 degrees Celsius. If you want to turn it into Kelvin, I think it's 289 or 298, somewhere there. The pressure is 1 atmosphere. If you want it in kilopascals, it's going to be 101.3 kilopascals. And then the concentration is 1 mole per cubic decimeter. And you cannot use the standard reduction tables, either table A or B, if you do not have standard conditions. Okay, it's very important, and that's why you have, if we go to E cell and you have that little zero there, that actually tells you that you have standard conditions. So if you don't have that zero there, can't use. Okay, if it's not under standard conditions, you can't use the tables. So it's very important that it is. Now 8.1.2, use a calculation to identify gas X. Okay, because the EMF is positive, we know that we have a galvanic cell. Okay, so we have one beaker or cell, and then you have your salt bridge. Okay, have your solution in there, and you have your rod. Let's say that's the aluminum rod, and well, the other one is a gas. Geez, I don't know how to put that, but yeah, let's just say there's a rod. And then you have your voltmeter there that will give you a reading of the EMF. Okay, and we said it's positive. Okay, hence you have a galvanic cell. And one part of it is the anode. I'm just going to put the anode this side. And then you have the cathode. So what happens at the anode? Well, an ox, so oxidation occurs there. And at the cathode, red cat, so reduction happens there. Okay, and where you have oxidation, basically you have your reducing agent. I'm writing all of this down because sometimes you can read a question, it asks for reducing agent, but when you read it, you think reduction. So it's just better writing down things that you know. So at the cathode, that's, we have the use of the oxidizing agent that helps reduction to occur. Now, we don't know whether aluminium is at the anode or at the cathode. Okay, and if they say use a calculation to identify gas X, we're basically going to use the tables of the standard reduction potential to determine what that is. And the equation we're going to use basically is E cell is equal to cathode minus anode. Ne? Yes. Okay. Cathode minus anode. Okay, now let us go to that table. You can use either A or B. It doesn't matter. Okay, really it doesn't. So let's say we use table A, which starts with fluorine and ends with lithium. Now guys, so when you look at this table, it is a standard reduction potential table. Okay, so the way they have written the equations is how it would be if reduction occurs. Okay, so if you were to write the reduction, if you were to write the reduction equation, you just copy it as it is from the table. But when you get to the negatives, okay, so positive, that's where you see. So with positive values, they tell you that, these elements or molecules or atoms, well, basically, they are easily reduced, if I could say. They tend to reduce much better. But when you look at the negative values, okay, that tells you that to reduce this, for reduction to occur, it has a tendency to oxidize. Okay, because this table just shows you the standard reduction, we don't have the standard oxidized potentials, we have the standard reduction potential. So these will tend to be reduced. Okay, they want to be reduced, and you have positive values. But the ones that tend to be oxidized, they have negative values. And if we were to write the half reaction of what happens when oxidation what happens when oxidation occurs, you're going to start writing the equation from the right to the left. Okay, and also when you write half reactions, please do not put double arrows, one arrow. Okay, so let's see. Let's go look for aluminium, and we'll see, is it positive or is it negative? If it's positive, it wants to be reduced, and if it's reduced, it's at the cathode. If it is negative, it wants to be oxidized, and you put it at the anode. So let us go and hunt for aluminium. Okay, so when I start looking there, aluminium. Oh, there it is. Okay, so we have aluminium, all right, and it is a negative value. So what is its natural tendency? Its natural tendency is to be oxidized, all right, so NOx. So we're going to put it way at the anode side. Okay, we had that the E cell is, okay, let me just write down the value. So we're going to subtract by, just hold this. Okay, we're going to subtract by -1,66. Ne? Yeah. And then, now question 8. All right. So at the anode, we know that we have aluminium there. Okay, its tendency is to be oxidized. So it will be donating its electrons over there. So it's negatively charged, but it's donating its electrons over there. Okay, and yeah, so that gas, what we put as gas X, is at the cathode, it will be reduced. Okay, so its volume here, it will be reducing. Okay, this aluminium. Ooh, now the word reduce. So it will be getting less. It will be getting slimmer. Finishing off, while this will be basically getting bigger. But yeah, so the E cell was 2,89 volts, right? And now we need to know what this gas is. So the cathode, where reduction occurs. So E cathode is equal to 2,89. So basically negative and negative will be plus, but if we take it to the other side, it's going to be minus 1,66. Okay, and then we are gonna just use the calculator and see what that value is. So 2,89 minus 1,66, and that is 1,23. Okay, so positive 1,23, so that is more likely to be reduced. Now let's go and have a look at the table. Where is positive 1,23? Okay, I see here we have oxygen gas. They told us it's a gas, okay, because we have two 1,23s. One is manganese, which is a solid, so no, we want the gas portion, all right? So we know that this is oxygen gas, which will be reduced to water, okay? So therefore, X is oxygen. You can write out oxygen, you can say O2. Okay, and indicate that it is a gas, so oxygen gas. And then now we go back to the question. It was a nice 5 marks. I think they were being generous, but that's nice. 8,1,3. Okay, it says write down the formula of the reducing agent in the cell. See why it was important to write all these things? Because if I hadn't written reducing agent in my mind, I would think write down the reaction of reduction. And yeah, so write down the formula of the reducing agent. So basically, if it's the reducing agent, that's basically where oxidation occurs, and that is the aluminium. And remember, I told you the table is written for reduction. So if you're going to look for what happens during oxidation, you're going to have to start writing it from the right to the left. Okay, so where's that aluminium? There it is. So we're going to write from the right to the left. So basically, aluminium, okay, which is the solid, we don't really need to indicate that, will be oxidized, and you are left with aluminium ions and the electrons, 3 electrons now. Yeah, 3 electrons. So that is what they want. Just reduce that. Okay. And yeah, where am I? 8.1.4. Yeah. So write down the half reaction. What was I writing before? Write down the formula of the reducing agent. Oh, I wrote the halves. Oh my goodness, I wrote the half reaction. They said write down the formula of the reducing agent. Okay, reducing agent in this case is aluminium. Okay, yeah. I guess it's just Al then. Oh my word. I wrote down the half reaction. Excuse. Yeah, so basically I wrote the half reaction and that's not correct. You must just write down the formula of the reducing agent, and the reducing agent is aluminium, okay, which is basically oxidized. Okay, that's it, not the half reaction, sorry. And then 8.1.4, it says write down the half reaction. Now here I go, I can shine now. Write down the half reaction that takes place at the cathode. Okay, so you know at the cathode, reduction takes place. You're going to take a look at your standard reduction potential table and you're going to write it exactly as it is. There's absolutely no need for you to turn it around. You're going to write it down as it is in heaven. So shall it be on earth. But yes, you write it as it is. So we said 1,23, ne? And it was oxygen. So we're gonna write it as it is. That's the half reaction. So we have the oxygen gas, okay, plus the 4 hydrogen ions, plus 4 electrons, and then show 1 arrow, and then it is reduced to water. Okay, probably a liquid. And this is all aqueous. Okay, it's fine so far. So yeah, as you can see, I'm just using the tables interchangeably. I know some of you are taught to use one table because of, whatever it is that the teacher told you. Whatever floats your boat, please do that. Alright, and then 8.1.5. Now it says write down the cell notation of this cell. What do they mean by cell notation? Well, basically when you look at this notation or this cell, you have half cells, right? You're starting at the anode. Okay, so you must talk about, or rather indicate what happens at the anode. Okay, so you're going to start here at the anode, then you'll indicate the salt bridge and finish off at the cathode. Okay, remember at the anode, that is where oxidation occurs. So you will start with your solid, it getting oxidized, and then you mentioned the salt bridge, and then you go all the way to the cathode. It is reduced to not a solid, but yeah, in this case we have a gas. So yeah, Okay, so let's do this cell notation. Okay, cell notation. We're gonna start first with the aluminium. Okay, and it goes and is oxidized. I think we had 3 plus. Can go check. Aluminium negative 1,66. Yes, aluminium 3 plus. And then we use double lines to indicate. Let me just, yeah. Okay, and then we use double lines to indicate the salt bridge, and then we go all over to 1,23. Yes, there we go. Okay, so we have the oxygen gas. Oh yeah, it's reduced. We write it as it is. Okay, and we finally get water from that. Okay, yeah, 2H2O. And I believe that's how you would plot, or not plot, but write down the cell notation. Okay. Yeah. Now the last question, 8.2. Okay, we're almost there, guys. It says, which container, zinc or copper, will be more suitable to store an aqueous solution of nickel ions? Okay, so you want the nickel ions to remain nickel ions. You don't want a situation where some electrons are released and then you have a reduced product. You don't want to leave your solution, then you come back the next morning and you find it to be a solid. Okay, so yeah, and it says, which of the two, zinc or copper, would be suitable to store the solution? So basically, if it's inside nickel, if the nickel is inside a zinc container, will it remain as a solution, or will it turn into a solid? Also, if it is inside a copper container, will it remain in solution, or will it turn into a solid? That's what we're looking for. So basically, I'm asking you, between the two, because remember, like here, where aluminium, okay, aluminium wanted to be oxidized. It has a natural tendency to be oxidized, right? So it was oxidized, whereas the gas was reduced. Okay, so we're gonna have a look then between copper and zinc. Okay, and we're gonna discuss and see which one is going to release electrons. You don't want it to release electrons that will react with the nickel. That's what we're really getting at here. And if it's releasing electrons, it means it is oxidized. Okay, so let's see. Between nickel, I can see nickel. Geez, I don't know if I can edit this PDF. Okay, but yeah. So this nickel, I hope you can see it, with a value of negative 0.27. Okay, and there we have zinc with a negative 0.76. Okay, so between zinc and nickel, which one really wants to be oxidized? Remember, because it's negative, it means its natural tendency is to be oxidized. If it was positive, its natural tendency would to be reduced, and reduced ones, they receive electrons. Okay, so between zinc and copper, we see that what do you call this? The potential for zinc, where is it now? Negative 0.76 volts. And then we have nickel at negative 0.27 volts. Now let's see, where is nickel? What is that? Oh snap, guys, what am I doing? Nickel is negative 0.27 volts. Sure, I was looking at the wrong thing. Where's copper now? Oh gosh. Copper 2 plus. Yes, copper 2 plus is positive 0.34. So if it is positive, it has a natural tendency to be reduced. Okay? Zinc has a natural tendency to be oxidized. Okay, meaning it is more likely to release its electrons, to give away its electrons. Copper is in a state to receive the electrons. Okay, now because nickel is in solution form, if it dares to receive electrons, it will react, and it won't be nickel 2 plus anymore. It will be probably a solid. Okay, so because zinc has a natural tendency to oxidize, it will release electrons even more than the nickel would. Okay, but copper, no man, it wants the electrons. So more than anything, nickel will thrive under copper's protection. Okay, so getting back to the art or the question, answering it, it says, refer to the table of standard reduction potentials to fully explain the answer in terms of the relative strengths of reducing agents. Okay, so basically, we go back where where oxidation occurs. You have a reducing agent. So zinc, it is a strong reducing agent compared to nickel, right? Copper, on the other hand, well, it is an oxidizing agent. Okay, it wants to be reduced, whereas zinc wants to be oxidized, and you can see there it's stronger, way stronger. Okay, maybe not way stronger, but it is stronger than nickel, and therefore it will oxidize happily. And if nickel is inside that container that is made of zinc, it will not remain as a solution. So guys, write something to get you the 4 marks, but basically comment on its ability to be reduced, its ability to be oxidized, which one wants to be oxidized, basically, by commenting also on the values, in the standard reduction potentials. They did tell you to go there, okay? And also comment with regard to nickel to say, Yona, it wants to be, it wants to oxidize, right? We don't want it to be reduced. So you rather put it in a copper solution where it keeps getting rid of the electrons so that copper can get, reduced even more, but it can remain in solution. Okay, try to put words there. Okay, 4 marks, you can definitely get them. And that marks the end of 8.2. Hello everyone and welcome to MV Tutors. I'm Solo and I'll be finishing off this paper with you guys. Question 9, we're almost there. I see an electrolytic cell. We already covered the galvanic cell, so let us get to it. So question 9, the simplified diagram below represents an electrochemical cell used for the electrolysis of concentrated sodium chloride solution. All right, so we have sodium chloride inside the water. So basically, when you have sodium hydroxide, which is a very strong base, and you react it with hydrochloric acid, which is a very strong acid, the two neutralize each other, and you have a salt, sodium chloride, which is quite neutral. Okay, pH of 7, basically, they're at the same quantity. So it's not like the acid and base question where the acid was in excess, but in this case, everything is like balancing quite nicely. Okay, so you have your sodium chloride in aqueous solution. Okay, X and Y are carbon electrodes. So if they're carbon, they could be in the form of graphite, which is mainly used because it is chemically inert. It will not react with the electrolyte being the solution, the sodium chloride solution. Okay, now let's start. Let's finish this off. 9.1. Define the term electrolysis or electrolysis. I think I like saying electrolysis. So basically, it's a process, right? It is a chemical process whereby you have electrical energy that converts or transfers to chemical energy. That's basically that. If you think about electrolytic cells, you're going from electrical to chemical. You need a power source. The fact that you have a power source there, which is like a battery or whatever, shows you that you need to convert electrical energy in order for the chemical process to start. Quite an expensive process on a large scale, right? Unlike the galvanic cell where it goes from chemical to electrical, quite nice. It happens spontaneously here. Not so spontaneous, hey? It needs some motivation. So we need electricity to convert or transfer to chemical energy. Okay, my nose is quite itchy, I don't know why. So that is electrolysis. I won't write it down, guys. As long as you know it's a chemical process whereby chemical energy converts to electrical energy, then we're cool. Then 9.2. Okay, I'm just gonna say electrical. Now I feel bad for not writing anything. Electrical to chemical. Okay, and all of this is a chemical process. Ooh, chemical process. Okay. Now 9.2. Okay, so 9.2 says chlorine gas is released at electrode X. So what is happening at electrode X if chlorine gas is released? Let's go have a look at the standard. Okay, we haven't even answered the questions, but I'm curious, before we even answer, if chlorine gas is released at electrode X, what is happening at electrode X? Okay, so we have our table of standard reduction potential. I'm looking for chlorine and I found it. So do you see the natural tendency in this table? Remember, this table shows you when reduction occurs or reduction takes place. So if reduction takes place, you have the gas, all right, taking in the electrons, and you have the chloride ions. But if chlorine gas is to form, we're going to go in the opposite direction. And the opposite direction is oxidation. So where you have your iron, it releases electrons, and then the gas also goes. Okay, so basically in this case, I stay in a loud place. So basically in this case, where chlorine gas is released, that's basically where oxidation occurs. I hope you understand that. So yeah, so at X, oxidation. Yes, X for oxidation. Now 9.2.1, it says write down the letter X or Y of the electrode where oxidation takes place. Well, we said it, X for oxidation. And what happens at the oxidation? Well, an ox, right? Just write there for yourself. At the anode, that's where oxidation takes place. So an ox. Okay, so we know the anode is on the right and the cathode is on the left. So X, anode. Okay, that's where oxidation occurs. Now it says write down the half reaction that takes place at electrode Y. So that's where reduction occurs, right, at the cathode. And if chlorine is there at the electrode, then sodium has to be there at the cathode. Okay, so let's go look for sodium in the first table. So sodium is right there at the bottom. All right, and we said that oxidation occurs there at X, so it means at Y reduction occurs. So however way it's written, that's it. We're gonna copy it as it is. Now where is chlorine? I mean sodium. So what did they ask for? They asked, okay, let me just write it down and then we'll go back. Now I forgot what they asked. Okay, so this is all aqueous solution. So we have sodium. Okay, let's just go back. What did they ask? They said, oh yes, the half reaction that takes place at the electrode Y. So there it is reduction that happens, right, at the cathode. Now 9.2.3, choose, okay, direction, okay, write down the direction in which electrons flow in the external circuit. Okay, so with your electrolytic cell, and I'm taking up a bit of time here drawing this. So you have your power source, and there we go. Okay. So just if this was the anode, I'm so used to putting the anode on the right, on the left, and the cathode on the right. So here your electrons are flowing from your cathode. Okay, by the way, this is a positive charge, negative, positive side of the battery. Okay, so your electrons are going to the cathode where there's reduction occurring, and here there's oxidation occurring, and you have your electrolyte which has sodium and chloride ions. Okay, many of them. So and we said oxidation happens at X and reduction happens at Y. I know they drew it the other way, but 9.2.3 says the direction in which electrons flow in the external circuit. Okay, so the electrons, they basically flow from X to Y. Okay, X to Y. By the way, you know, I already covered this lesson there in the YouTube. So as normal,
because this electrode is connected to the negative terminal of the
so you
battery,
see for
its
yourself,
charge
me and Dukes. But yeah, so basically you can go to the chemistry lessons, the playlist, and you will see the lesson right at the bottom, to master electrolytic cells. Okay, and I also do some practical applications of electrolytic cells if you're interested. That was a little bit of an ad break. Okay, 9.2.3. Yes, we said that it would flow from X to Y because X, that's where oxidation occurs. Your electrons are going to go away to the other side where reduction occurs, and so it goes from X to Y. Now 9.2.4, write down the balanced equation for the net overall cell reaction that takes place in the cell. So for us to write the net overall cell reaction, we first need to write down what happens during oxidation, what happens during reduction, and then finally add it all up and see what's what. So we know that oxidation, that's where we had chlorine, right? There it is. Okay, so oxidation, we write it from the right to the left. So we have 2 of the chlorine ions or chloride ions, and then we have chlorine gas plus 2 electrons. Then we go over to sodium. And guys, here's very important to balance, right? We need to have the same amount of electrons. That's how you know that things are balanced. So sodium, here it is, because it's reduced, we write it as it is. So we're going to have sodium plus an electron, and we get sodium, right? Solid, this is okay. So here you have 2 electrons, and here you have 1 electron. So how are you going to balance this? Here you're going to multiply by 2, and there you're just multiplying by 1. Okay, and so if you multiply by 2, what are you going to get? I'm going to multiply by 2 throughout. 2 electrons, 2. Okay, so now we can finally write down our full answer. By the way, with the full answer, you don't include electrons, okay, because they'll basically cancel out. You have 2 electrons on the left hand side of the arrow, and you also have 2 electrons on the right, so they basically cancel. And what are you left with? You're basically left with 2 chloride ions and 2 sodium ions, right? Okay. And then on the right hand side of the arrow, you will have chlorine gas, which makes sense, right? Chlorine gas was the chloride ions were oxidized and you had chlorine gas as a result. Then you had the sodium ions, which were reduced to give you sodium. So 2 times the sodium. Okay. So basically, guys, this is like your, let's go back. This is your balanced equation for the net overall cell reaction that takes place. Okay. How many marks is this? 3 marks. Yeah, I think this should be worth 3 marks. I think on the side, maybe you might want to write how many volts this chlorine is, but not. You can. I don't know if they're going to give you marks for that or if this is sufficient, but I believe it is. I think this is really worth 3 marks. Now let us continue. How will the pH, 9.3, how will the pH of the electrolyte, remember the electrolyte is basically the solution, okay? The sodium ions and the chlorine ions. So basically, how will the pH of the electrolyte change during the reaction? Remember when this video started, I said with sodium chloride, basically you had sodium hydroxide, which is a strong base, right? pH above 7, which reacted with a strong acid, which is hydrochloric acid. Okay, strong acid. So that strong base and that strong acid, they came together and they neutralized one another, and you ended up with a neutral solution. And because it's a neutral solution, it means the pH is 7. Okay, so whether or not electrons flow from left to right, okay, they're actually going from X to Y, that's it. Your pH will remain the same. Okay, if they added more hydronium ions or whatever, then maybe the pH would change. Or if there were more hydroxide ions or whatever the case is, yes, probably the pH would have changed. But from the standpoint of sodium and chloride ions, it still remains neutral. So it remains the same. Okay? And if they ask why, well, everything that I've just said now. Yes, your listening skills. So it remains the same. Due to the strong acid reacting with a strong base, producing a neutral product. So the pH remains at 7. That's the reason. And we are done. I can finally go and do my assignments that are due very soon. But I hope you guys are ready for paper 2. I'm recording today, Friday. Monday, you're writing. As for the matrix, you guys will be writing your paper. I don't think it'll be involving all these topics, but do pick up from the sections we've covered what you need to cover for your matric exam. Otherwise, it's good night from me. And again, don't forget to like our videos and subscribe to our channel and tell a friend about this amazing channel. Bye.